Like for example, if you get burnt on the Mercury, you turn all these other tests, and there's a quick way of validating that what you do, the code that you have is not the code that you have. But you have to learn what the you're trying to validate the code for the whole team. Yeah. But you can, in the unit test file, you can shut off, you can just comment out which file, you want to skip so that it's so like for example, if you just have, if you're just running like an off function with a PO2 or something, you don't have your fixed stuff, it's just putting a pound sign in front of that's commenting out a line of file. Very, very customized. Any other questions? Yeah. We often update it, but usually for purposes of, for operational purposes, we'll download a unit test that we take to a given benchmark version. So like if we want, like when we use 1101 code, we can get the unit test data to correspond to that code, and then we can upload. Sometimes we do get into a development stage where something that happened easier to fix. Most of the time, most of the fixes that we put in the benchmark model version are just getting so it's pretty safe that like whenever if you're upgrading from level A to B to C, to pull the unit test with that point. Very often the implicit is different because like sometimes the MCO configuration file is different or whatever. So like we always make sure to put those updates in the unit test data. So I would update the Yeah, so version 11, if we downloaded the version 11 public release, that is sort of, we keep our development unit testing separate from the unit testing that ship to version 11 public release. Like if you were developing off of like one of our branches, like 1103, you could actually get the latest updates from our development talk a little bit about Tempo. I did talk a little bit about Tempo is just, I have stuff about file. Okay, so as we've heard about FlexPen, it's a purely implementation of KPP, so all the stuff that we hated about SMP for the prior models, like, the C though it's, for example, the version 11, there are 5 out-of-the-box mechanisms that you can pick from that come pre-built with Flex. So there's a traditional focus wheel kind of configuration out of the box. Not that what's done on the focus wheel. So everything's been kind of added to the front. There's also very good IGC8 and then there are a couple of SLA secondary but our standard simulation, the ones that we report the basically both template DCX with SLA. This is what we have done. So when you run the standard out of the box, so if we wanted to, if we wanted to get into the guts of the solver, modify the file. All those key files, make the changes, run the code, run the file, so it's much easier. The point is the file format in KPP is a lot easier, more transparent, much more sane, I think, than in the old SMPP ones. So it should be much easier. You can change, like in Rosenbach's default, there are several options. There's like also, there's like setup. If you look at the blocks, keynote is at 1:30, so I think I'll wrap it up here. But we have office hours. I believe we're going to be at the end of the hall. Go out the door to the left and all the way to the office.
It should be on, yeah, it's on.
Sounds like it works in here when we're using it like this. Okay. Is it working? It's test 1, 2, 3, test. Test. We're boosting it? Okay. Like here? Is that, yeah, so you can't hear it. It's very low. I don't know what to keep saying, so okay, here's my guess. Test 1, 2, 3, test 1, 2, 3, test 1, 2, 3, test 1, 2, 3. Do we, testing, testing. Test 1, 2, 3, test 1, 2, 3. Wait, do you just keep... Yeah, test 1, 2, I'm assuming you're over there, Danny. But test 1, 2, 3. Test 1, 2, 3. Test 1, 2, 3.
So if you want to go in and see if the other room sounds good. Okay, yeah, because so far this seems to be. working okay. And we'll see if it works out in G125. And we're still doing a mic test here. Still doing a mic test. This will sound actually louder back there than it does in here. It sounds very echoey. You're kind of like in a pit here, so it kind of doesn't. Are you not connected or just?
No, because he's going from his own computer for the first one.
Right. Okay, but it's not connected right now.
Restarted.
Oh, okay. Okay, so then we'll see. Okay, and that happens. 1, 2, 3, 4. That seems to be working okay. 1, 2, 3, 4. 1, 2, 3, 4. 5, 7, 18, 25. Seeing if this works in G125. Okay, it works better now? Okay.
Good? But there is sound.
This sound, it works.
Okay. All right, the batteries look good.
Baron, it should be working now whenever you're ready. You just have to, hold it up like kind of close.
Okay.
Whenever you want to start.
What's a good way to get people's attention? Just go with it?
Start singing.
All right.
Whatever you want to do.
I'm not going to start singing. Hello? 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 Okay, I have the honor of introducing Paul Wimberg, who wanted to start just a little early in case he goes just a little long. He asked me to keep it short, so I'm just going to say that the MacArthur and AGU Fellow, as also the Stanton Avery Professor, the Director of the Lynn Center for Global Environmental Sciences, a Harvard and Oberlin alumnus, a Vermont native, and played the bassoon until kids made him too busy. So with that, I will let you take it over.
Thanks a lot, Baron. And thank you very much to the organizers of the meeting and to Danielle for inviting me to come and present today. Okay, so I thought I would, as one of the few experimentalists here, although Jose is also, there's a few of us, I thought I would tell a little story today about how we interacted with GSChem and both how we think we've maybe provided some guidance to the model development, but importantly for us, to show you a little bit about how it guided our own decisions about how to spend our time, which, as all of you guys know, is probably the most important decision you make. There's a lot of interesting problems, but using a model to tell you where the sensitivities lie, sensitivities in the atmosphere, that is, I think it really helped us to guide the kind of lab work we did. And in particular, I'm going to talk today about research in my lab that has been looking over the last decade, really, at the photochemistry of isoprene. And for your consideration, see, I'm in LA now, so this is the sort of language from the Academy Awards. We hope that something like what we've developed will be implemented in the fall version of I guess it's called 11.3 maybe. But anyway, we'll see where we get. And so again, because this really has been this interaction between us and the community here, I really would like to thank Danielle for making this model open sourced and available in a way that even experimentalists who aren't really programmers can use this tool. And so this is the paper. It's an enormous effort with many co-authors. It's going to be submitted this summer. And it's our attempt to synthesize all the lab work that we've done in our group over the last decade, and including work that's been done outside of our laboratory as well, that has really refined our understanding of how isoprene is degraded in the atmosphere, what major products are formed, and their subsequent chemistry. This story actually begins with Jesse, who's here. And actually, he's wearing the same sweater. I think it's true. So Jesse Kroll. Okay, so Jesse Kroll was a student of Jim Anderson, as was I. So we are brothers. We are brothers, academic brothers. And Jesse came to Caltech. Oh, look at this. I inherited my hair from Jim and not from Jesse. That's a good thing. Okay, so Jesse came to Caltech to work for this guy, John Seinfeld, to do photochemistry experiments in the environmental chamber at Caltech. Now, the chamber was really an engineering effort to understand how much organic aerosol forms when you degrade various compounds. That was really the whole idea, and really the intellectual force particularly for John's group. But Jesse was, I think, maybe the first chemist to go work for John Seinfeld. Chemist meaning as in a physical chemist. Somebody who actually cared about what was the black box that related the input, say an organic compound, and the output, which would be the aerosol. And so in that, he brought to John's group really this idea of understanding much more about the peroxyradical chemistry of organic compounds. And it was there where we really began this work. John Krauts, who's a longtime collaborator and member of my research group, just a fabulous experimentalist, developed techniques to measure many of the oxidation products of the degradation of organic compounds. And as such, this was a natural collaboration, and Jesse came over and said, hey, John, let's bring your instrument over, and we'll do 4 experiments. They ran 4 experiments that made up Fabien Polot's thesis. So there were a lot of things in that, but it was really based on 4 experiments where the isoprene was degraded at both very high NO concentrations and then essentially in the absence of NO. And so that's Fabien. Many of you know Fabien. He's not here. He's moved on to other modeling tools, maybe. Fabien Polot, he was French, so that's not necessarily a bad thing. But you have to understand, French people don't really do experiments much. I think Daniel might agree. But he was exceptionally good. He was a scholar, and is a scholar, and very good at thinking about programming and how to put together these tools. Anyway, he came to work for Mike Hoffman. Mike Hoffman is a sort of old storied person of our community. He worked on cloud water chemistry with some other guy. Danielle was Michael's student. And so Fabian and Danielle are brothers. I have yet to figure out, because Fabian's my child, that makes us. Anyway, okay, so this group of people did this experiment, and they did 2 low NOx experiments, which I'll tell you about in a minute, and they did 2 other experiments that were high NO. And believe it or not, we understood the high NO chemistry pretty much right away, but it led to this completely crazy paper, which many people look at it and they just go, oh my God, this is so damn complicated. And if you ever try to put that into a full mechanism like that into a model, in the old days it got really bad pretty quickly. Things slowed down to glue. Anyway, so we wrote this paper, or Fabian really carried the ball here, on the high NO chemistry, but we didn't understand the low NO chemistry. Because what we saw was, just as you might have predicted, you make hydroperoxides. Hydroperoxides that were incredibly reactive, or so everyone would have thought. And we were measuring this signal that John Krauss had figured out how to measure, and it didn't go away nearly as fast as we thought. The hydroperoxides came in as expected, but they didn't go away. And this took us a long time to figure out. And so I'll tell you that story later. I need to stay with the NOx for one more story here. So this was our first interaction with GS Chem. And in this interaction, Fabian, working with Davin actually. Okay, so what we wanted to understand was what makes the atmosphere so sensitive to the way you write down the isoprene mechanism. And the atmosphere is incredibly sensitive. So this was just a thinking experiment. We said, let's imagine everybody in the world emits NOx like North Americans. What would happen to the ozone in the troposphere? The whole column. And in the tropics, you can see it almost doubles. And the reason is there's a lot of isoprene in the tropics. And there's actually a lot of people there too. They just don't emit much NOx right now. But they will. They probably will. And when they do, it's going to cause, or maybe it's already causing, a substantial increase in ozone levels there. And so the question, though, we had as chemists was what is the reason? Because Fabian did this experiments where he modified the isoprene mechanism, forward models, and then in reverse, and asked how can you change this picture depending on how you write down the mechanism? And the answer was you could change it enormously. And in the end, this was the figure that came out of that paper. These are all different forward models where we just changed one aspect of the nitrate chemistry. And you could get 40% changes in the production rate of ozone across the globe, depending on how you wrote down the mechanism. And why was it? It turns out it was all about what happens to NOx. And I think in general, this sort of reinforced my view in many ways about the way photochemistry works in this atmosphere. It's so dominated by the NOx sensitivity. So we're going to hear about halogen chemistry later. And I'll bet right now most of the response is going to be because of what it does to NOx. That's just a hunch. And so then you realize in the context of a simulation and a modeling exercise that you've got a huge knob right here. So you can compensate for anything you want in this chemistry by turning your NOx knob. And so the question is, what are we doing this for? And I think the answer should be, well, we should try to put in the chemistry as it's right. And then at least know why we're turning a knob. Where in this case, you could have a big error in your NOx sensitivity, and you could get perfectly good simulations by turning the NOx knob. But you don't know whether that's going to be the case in the future. Is that knob different than the future knob? So that was one of the first things we learned, is that we really needed to think about this nitrate chemistry through its impact on NOx. And so one of the big knobs in here that leads to this big divergence is the formation of what are called these hydroxynitrates. These are 4 examples of these hydroxynitrates that form in the isoprene mechanism. And there's been a long debate, running debate, about what the yield, what fraction of this chemistry goes to form nitrates. We now know the answer is 13%. This is not a number that GS Chem is going to like. Now, they've been low forever, and they've been creeping up towards us, but it causes all sorts of problems. But the answer is 13, and if your simulations produce the wrong answer, it's for some other reason. It's not because the yield is wrong. And we'll talk about this later, or we can talk about it offline, why we think we're right, and why we understand why the other measurements fall in the way they do. But the answer is that within a few percent of 13. Okay, this was work that was done by a really great graduate student, experimentalist Alexander Tang, and it just was published this last week in JACS. And so I refer you to that paper. But again, John Kraunz was the key to making this all work, and you'll see that's a real theme. The second thing we realized, of course, through our modeling with GS Chem and also with CMAC, was that only about half of the nitrates are calculated to come via the NO chemistry. Almost as much comes through NO3 chemistry at night. At least in the United States, that's the case. And so the next thing was another great graduate student, Becky Schwantes, worked on the chemistry of NO3. And again, we worked through this rather complicated mechanism that's all then being synthesized into to the larger mechanism that Kelvin will tell us about later. And of course, John Kraunz. So I told you a little bit about this story. This was the low NOx chemistry now. And again, what we had seen was that the formation of these epoxides, of our signal, happened quickly and then decayed very slowly, much slower than we thought. And the reason is that the chemistry, as now we know, is that you first form these hydroperoxides, the ones we thought we were forming, but then they go on in the next step to form epoxides that have exactly the same mass. And because we're using a mass spectrometer, we couldn't tell them apart without going to some more tricks that John Kraunz figured out how to do. And so we ended up realizing then that the chemistry was much more complicated, and of course this leads now to a lot of conversation about the importance of such compounds in the formation of secondary organic aerosol from isoprene. And I still think there's a lot of confirmation bias going on out there. I think you should be incredibly critical of a lot of those papers that are out there. There are a lot of mass spec that will produce very similar fragmentation from lots of different compounds. And if we like to think it's solved, these are very volatile compounds. And so I think everyone should read that literature very skeptically and think about what they're doing and what they're really simulating. Okay, that's just an aside. Kelvin. Okay, Kelvin, among many things, this is Kelvin Bates, is an exceptionally good singer. And he was the lead in the Caltech play, Star Trek play that was written at Caltech called Go Boldly. And he was perfectly cast, I think we can agree. Don't you think? I mean, really. And so Kelvin showed not just which IEPOX isomer you form, but he showed which of the 2 isomers form. And this is another thing that turns out to be quite important, because these compounds have really different properties. Their vapor pressures are enormously different. One of them is easy to handle in the lab. The other one is like glue. So I think we can understand that maybe we should think about them separately. And so, again, this guides our development of a mechanism for GS Chem. We're trying to say, when are things chemically different enough that you really do need to treat them separately? I'm probably almost out of time. Okay, so we followed this up with a paper that involves this guy, Frank Koich. See, Caltech has the best photographer. I mean, Harvard has really good photographers. Look at that. Yeah. But this is Gene. So Gene Rivera-Rios, who's somewhere here, there he is in the back, working with Frank, synthesized peroxides. And for those of you who are not lab people, these things explode. Okay, so this is not the kind of thing you want to do without knowing what you're doing. And fortunately at Madison, there was a very good chemist who knew how to make these things. I hope that Frank has such luck here to have a colleague who will help him synthesize these amazing compounds. But they brought him to our lab, and we were able to do photooxidation experiments with the individual isomers. And this is all then being integrated into this paper that's coming out and into the mechanism, where we, again, try to keep track of the carbon. Okay, so this is another little bit of an aside, but I wanted to show you. This is the amount of epoxide formed in Fabian's original synthesis in GeoChem, and then in the latest. And I think the scales are basically the same, the color scales. And so you can see that we now have quite a bit more of these being formed than we used to. And why is that? Well, when we started working with GeoChem, I think Danielle would agree that the chemistry had sort of sat a little bit dormant for quite some time. The focus on the model, not like it is today, but on emissions, dynamics, and all these other things that are critical to getting it right. But the chemistry itself had been sort of not really following the literature. And CMAC actually turned out to be no better. So in the GeoChem mechanism that Fabian used, I forget what version this was, but the isoprene peroxy radicals reacted with HO2 at the same rate as methyl peroxy reacted with HO2, which turns out to be like a factor of 2 to 3 too slow. And so in those simulations, and in the Larry Horowitz's paper on the nitrate yield, that one he had everything reacting with NO because the HO2 rate was so slow. And so he had much more NO chemistry than was really happening. And so this is where we, I think, started to give back a little bit to GeoChem, in the sense of, chemists looking at the mechanism and trying to understand the history of it and helping to guide the changes. Maybe Daniel would agree, I don't know. But this was one of the first things we identified, was that this was not a good idea. It wasn't good to have this rate being off by a factor of 2.5. And so, again, that's pretty much why most of the chemistry is really HO2 dominated in the tropics, whereas in the older simulation, NOx had played a much bigger role. Okay, so that led us to a new idea, which was really, what really matters is the ratio of the rates with HO2 and NO when you think about this chemistry. And so with Jeff Tyndall now, we've done oxidation experiments of a whole suite of hydrocarbons, looking at the relative rate of reaction with NO and with HO2. And this is coming soon, and I'll tell you that there's no earth-shattering relationship here. It behaves pretty much like the literature, if you had read it, would tell you. And so that we don't think it's going to cause a huge change in the mechanism. Okay, so back to Kelvin again. Kelvin then next looked at the degradation of the epoxides, the gas phase. The solution phase chemistry had been studied in detail because there's so many people interested in SOA. But it turned out the gas phase chemistry had not really been studied. And so we measured the rates and the products that form from this chemistry. And you can see, again, it's a pretty complicated system, but one which you'll be able to get a KPP file that will read it all in for you. At least that's our goal. And then the last really big piece of this has to do with what happens to the peroxy radicals when they first form. And I don't know how many people actually have followed this literature, probably not so many in this community. But when you add OH to isoprene, you can really add it in only 2 places. It adds, in this case here, at the 1 carbon. And it leads to these allyl radicals here, allylic radicals, that then add oxygen, but they can add it in several different ways to form a suite of peroxy radicals. And unfortunately, the bond strength of that O carbon bond is pretty weak. And so these things fall apart and reform all the time in the atmosphere. And so things that we thought were like constant, like what's the MVK yield from isoprene plus NO, turns out it's not constant at all. It depends on how much NO you have in the system. And because most of the lab work had been done with very high concentrations of NO, you end up with a yield that's not correct. So you actually need to put in some very complicated dynamics to correctly describe this chemistry. You don't want to do that in GeoChem because that'll really slow it down. And so we've worked out some schemes that allow you to essentially describe this chemistry in a much more compact form. But you do actually have to do it, because if you don't, you'll end up with the wrong answers. And so and Kelvin will show you some of the details later. So we measured those things. We also measured the rate at which there's this interesting chemistry where this oxygen pulls off a hydrogen on the same molecule, leading to formation of these things called hydroperoxyaldehydes. We've worked out the rates at which those form and their yields. And the yield of those is low. It turns out that the yield's only about 1/4. and we can find some of the other carbon, but not all of it. And so this is going to be remaining a big uncertainty, at least as far as isoprene chemistry. What is formed in this chemistry, and what does it do? And so there's still work to be done for those of you who thought isoprene was finished. We then worked on the methacrylin and MVK chemistry, and again, they behave in ways that we had not anticipated. Methacrylin undergoes a internal hydrogen shift chemistry that leads to the formation of hydroxyacetone, almost entirely from the OH addition. All the chemistry we had in GS Chem was completely wrong. And then on the MVK side, on the chemistry here, leads to the formation of MPAN. And I know there's a talk about MPAN coming up. But again, a lot of the chemistry that we had in there really was not properly describing its photooxidation. So I'll be interested to see what happens in the future. And then, as I mentioned, finally, MVK, this is Eric Praske who did this work together with John Kraunz. And we discovered, again, that the peroxyradical chemistry, in this case, leads to very high recycling of OH. And so, again, the theme, I think, of what we've learned in many ways is that the isoprene chemistry is much less of a sink for OH than we had anticipated when we started this whole work. And so, coming again to you near this summer is this synthesis where we've attempted to put this together in a mechanism that has three major goals. One is to keep track of the carbon. We didn't like the idea that a lot of these mechanisms lost carbon. So we're trying to maintain carbon balance. We're trying to implement the chemistry in a compact form in a way that preserves the important chemistry that leads to secondary organic aerosol compounds, and also to the impact on NOx levels. And so that, we hope you will enjoy that. We're going to probably send it out for beta testing so that we can try to uncover as many bugs as possible before it gets published. And then finally, the last, where I think the bodies still are laying is, we really don't know all the products of this chemistry that encompasses about a quarter of the total global flux of isoprene. So it's not a small amount that's going this way. We don't know what the rules of OH recycling are. And again, we've measured in a few systems, but then how do you extend that to this broad range of substrates? We don't really understand yet when do you recycle OH. The nitrates, we've measured them for a few, but again, the substrates are so varied. In some cases, we know the nitrate yields are quite low. And so there must be some rules there, and I'm in sabbatical in Copenhagen right now working at a computational chemist, and we're trying to figure out what these rules are and how you would describe them, because otherwise you'll end up with lots of higher order nitrates that may not form if you just simply implement the sort of standards. And we don't know what the fate of these are. We have measured now the rate at which the major isoprene nitrate reacts in water, and it's incredibly fast. And so one of the isoprene nitrate isomers will react instantly and the other will never react. So it's kind of weird. And again, it guides our mechanism development because you really need to keep track of those two separately. Otherwise, you would end up with perhaps the wrong idea. So my group, as of a year and a half ago, and I've had a great, amazing group of students working with me on this kind of chemistry. And this year I started my sabbatical with 8 students, and I'll finish it with 3 because the 5 of them have graduated. Kelvin, who's up next to show you the impact of this chemistry, will graduate, well, he'll defend, I guess I shouldn't prejudge it, on Friday. And with that, I'll thank you again very much.
We've got time for maybe one question.
Dylan.
Paul, are there other compounds, so this reversible O2 addition, and are there other sort of compounds in the atmosphere where that would be important to think about, like aromatic compounds, or is it?
Yeah, I think aromatics are one area where that's definitely going to be the case, and really needs to be thought about. You know, there's these cyclization reactions that happen in aromatics, but apparently those lead to bonds that are pretty strong. They break the main aromatic resonance, and so once you form those, they probably are very, very stable. But I think it may be that we have underestimated the formation of those in the atmosphere for just that reason. Because the non-ring forming ones probably go away. And so I think that is an important area for butadiene will do the same thing. And there's a couple of the terpenes that have this, you have to have this conjugated double bond thing to form these allylic radicals. I forget, there's one, you probably know which one is the terpene with the conjugated double bonds. Limonene or something, anyway. There's several of them. Yeah. Kelvin.
All right, thanks. I'm Kelvin Bates. Now you guys know more about me than I would have liked. I'm a grad student at Caltech with Paul, where we study the oxidation of isoprene, among few other things. It's really been mostly isoprene for a long time now, in the gas phase and a little bit of its particle formation too. Paul already gave you a rundown of a lot of that chemistry, so it's my turn to tell you kind of what that means for actually plugging this into the model. Like Paul said, we've spent the last many years, really, compiling this big explicit isoprene oxidation mechanism in an effort to synthesize all the work that we've been doing and other groups have been doing on isoprene over the last decade or so, and come up with a coherent set of recommendations for how to treat this in, say, models. And I'm not going to go into any more details about what that chemistry actually is than Paul touched on, except to say that we have recommendations that will involve changes from what's in there now to pretty much every aspect of isoprene's chemistry, from its initial reactions with ozone, NO3, and OH to what actually happens to those peroxy radicals that form once you react with OH down all of those pathways that Paul was showing earlier. So when we put this whole thing together, we get a whole bunch of figures. This is just a few of the ones that are in that paper. And at my last count, we're up to something like 261 compounds and 500 and some reactions, which obviously is not terribly useful for something like geochem. Ideally, we want something simpler than that. So that's what we've been working on most recently, is simplifying that down, coming up with a more condensed mechanism that is viable for people who don't feel a need to know what happens to isoprene, but do want to know the importance of isoprene for various things that matter to atmospheric chemistry in general, such as oxidant budgets, the transport of NOx through isoprene nitrates, and how isoprene contributes to aerosol formation, among other things. But these are just some of our big priorities as we condense down this mechanism, and in the process make sure to retain carbon and radical parity, not lose any products that might contribute to the carbon or radical pool. We try to keep explicit treatment of any products that are made in at least 1% overall yield from isoprene, though we might cut that down a bit, and including treating separate isomers if they do have separate subsequent chemistry as well. And then not leaving any dead ends in the process if we come to a compound that we don't have a recommendation for, deferring to its nearest analog or to things that are in MCM right now. And so at the most recent tally, I have this down to, 64 compounds, hopefully getting smaller than that, but that's what the results that I'll be showing you are from right now. So to get into a little bit of what that actually does to the model, these are all annual averages right now. When I compare to a baseline mechanism, I'm comparing to what ships with version 10. And for those of you who don't study isoprene all the time, it's emitted by trees. This is a map of where that happens. So when you see maps of what isoprene chemistry does in the atmosphere, they usually look something like this, but in different colors, basically. So first look at what this does in the atmosphere, what happens to isoprene. Our new mechanism doesn't cause many changes in the initial oxidation pathways of isoprene in terms of ozone versus NO3 versus OH chemistry, but we do see a significant increase in the fraction that of those peroxy radicals, RO2s, RiO2s in our mechanism, that isomerize at the expense of reaction with HO2 and NO. And that's important because the isomerization channel, which Paul was talking about, forming those hydroperoxyaldehydes and other subsequent products that we don't really know yet, but we do know that it's pretty efficient at oxidant recycling, and so this has big implications for OH concentrations in remote areas where that chemistry happens. We also now speciate these RO2 radicals to their different isomers, which Paul touched on is important because those different isomers actually have different subsequent chemistries. And the reversibility of oxygen addition means that this pool of RO2 isomers is a dynamic system that evolves over time, and depending on your radical lifetime, you'll get different distributions of these isomers here. So when we allow for this equilibrium to come into effect, rather than the kinetically limited distribution that was usually incorporated into models before this, we get much more of the products reacting through their beta channels, the 1,2 beta in particular. That's 1 OH and 2 peroxy in terms of the carbon position of those substituents. That ends up taking up much more of the radical pool, and what that means in practice is that you make much more MVK than most of those old studies with a really high NO would have predicted, and much less methacrylin relatively. So this is one of the biggest changes that we see when we plug in our new mechanism, is a huge change in the relative ratios, at least, of MVK and methacrylin. In terms of other VOCs that we look at, we spend a lot of time looking at SOA precursors, and so we think we do a better job treating IEPOX and MPAN, two of the biggest SOA precursors from the low NOx and the high NOx, or low NO and high NO, we prefer, pathways. But we also now explicitly treat some of the highly functionalized compounds that we have long suspected might form from these channels, but haven't really known well enough to actually treat them explicitly in these models. When we do, we think we see a whole lot of them actually forming these dihydroxy dihydroperoxides, iso-POO2, I didn't make that up, and the dihydroxy dinitrates, which are still, like Paul mentioned, very uncertain exactly how much of these form. But it turns out they're probably going to be important because we think a lot of them potentially get made on the order of 50 teragrams a year, which could contribute a lot of aerosol formation from isoprene. And in what little time I have left, I also want to show a little bit about what this does to other things that you might be more concerned about, people who don't study isoprene, I guess. So isoprene nitrates contribute substantially to the transport of NOx out of forested areas where isoprene is emitted, and to more remote regions. We'll hear some more about PAN in a couple minutes as another mechanism of doing this. But our increased isoprene nitrate yields substantially increase this NOx transport. Now there's other factors that might play into this, like what happens to those isoprene nitrates, how much heterogeneous chemistry affects their subsequent fate rather than, say, photolysis or subsequent reaction that might release that NOx. So there's still a lot of uncertainties here, and a good deal of knobs that we can turn to tune this result, I guess. But this is what initially comes out when you turn up those isoprene nitrate yields. We also see smaller changes in ozone formation from this new mechanism, but much larger changes in OH production, and that's largely because of that isomerization chemistry that I was telling you about earlier, that now plays a much larger role in remote regions like the Amazon and, to a lesser extent, the Congo basins, where a whole bunch of these isoprene peroxy radicals react through this isomerization pathway, efficiently recycling the OH, and you get much higher levels of that there. So I think that's all I've got right now. There's obviously a lot more to this chemistry. I'd be happy to talk with any of you guys about that later on. I'll be coming here in a few months to work more on plugging this into Geoschem and seeing how we can effectively represent it while keeping it simple, hopefully. Yeah, thank
We have time for a couple questions.
So I am curious about whether you've looked at any comparison to observations, and in particular, when you dial up the yield of the isoprene nitrates to 13%, what do you do about the fate of those isoprene nitrates?
So yes, that's the big next step for Geoschem. We've done a lot of comparing to observations in the smaller scale of say, box model kind of things with this, and looking at the different isomers, because we can now speciate the different isomers of these isoprene nitrates. And we can tell that we're seeing a lot more of the ones that we observed in lab and that we think should be there. But what happens to those individual isomers? Some of them seem to go away much faster than others, which is part of why people haven't observed them in the past, but it's also kind of an open question for what happens to them in the atmosphere. So that's the big next step, I think, in determining, what happens to these isoprene.
So do we get rid of the holes in the OH of the Amazon?
Yeah, pretty much, from what I can tell. Although we know there's so many other, I mean, who knows what happens when we plug in halogen chemistry now. Like, I think this is going to be the big knob to turn over the Amazon, for sure. But there's so many other factors going into this.
One more round of applause. And next up we have Emily Fisher.
Use the mic. Okay. This is actually going to be a very simple talk, I think, compared to the last two. So maybe that'll be a relief for some of you. I'm sorry that I'm not going to talk about MPAN. I have some other challenges related to that, but I won't talk about them today. So I started working on the PAN simulation when I was here. It feels like a while ago now. And here is a figure from that old paper. And so here I have the upper troposphere and various seasons. And what I want to point out are different features in the global PAN distribution. So the first one that I want to show you is an austral spring maximum. And so what you're looking at here are the contours are not necessarily linear, and the model is shaded and the observations are circles. And so the model shows that there's a lot of PAN. They're sitting over the tropical Atlantic in spring. So the second feature that you can see from plots like this is that the model produces a reservoir of PAN aloft in the northern hemisphere summer, and you can see that both where I have it circled here, or squared in pink, and then above in higher up in the atmosphere. A better view of this is in an altitude-longitude plot, so you can see this is average PAN 30 to 60 degrees north, and there's essentially this river of PAN in the model floating around the northern hemisphere in summer. And so right here is North America, that would be Europe, and that's East Asia, right? So the third thing that's popped out in this old simulation is that there's a lot of PAN leaving Russia in springtime. And so the model tells me that boreal fires are important in spring. And so what I've been doing over the last couple of years is trying to figure out how to leverage new test PAN measurements to both verify these things and understand what's contributing to these features. So are they real, and what contributes, and then whether the model gets that or not. So this has been tough because it's really hard to measure PAN from space, as it turns out. Probably someone with more of a background in this could have told me this at the start. But so the spectral signature of PAN is weak and broad, and so TESS is only sensitive to PAN in the mid to upper troposphere, which is why on those maps I only showed you the mid to upper troposphere, or away from the boundary layer. There's only less than 1 degree of freedom for signal, so we only have really a 1 point piece of information, no vertical resolution, the errors are big. TESS only sees elevated PAN, so our detection limit is somewhere around 200 ppt. So these are only PAN plumes that can be detected from TESS. But that being said, for the first time we have this ability to look at interannual variability and to have a lot more data. Okay, so the rights and wrongs. So here's the first right, which I was very excited about when we saw. So what's shown here on the top, this is a new paper from Vivian Payne. The gray points are attempted PAN retrievals from TESS, and the colored points are the points where PAN was detected, and it's colored by amount over here on this scale. On the bottom here is the fraction of measurements where elevated PAN is detected. And so look, in the tropical Atlantic, there's a lot of PAN. And so that I would say is right. Now the model attributes this to lightning, NOx, and then isoprene oxidation products. And I thought when we wrote this proposal we would have these beautiful pan-CO correlations, and I would be able to figure out or distinguish between lightning and biomass burning sources, and we can't. So I still think this is a lightning plus isoprene signature, but that's there. Okay, So number 2, the River of Pan. So this is a new thing that I've also learned. So here we're looking off the coast of Western North America. Here's April and here's July, so 2 seasons. All the dots here are successful test pan retrievals. So these are plumes that have crossed the Pacific in some way. The top here, they're colored by the retrieval day of the month. And the bottom, they're colored by the tropospheric mean pan. The point here is that there's a lot of trans-Pacific transport of pan in summer. So when we think about trans-Pacific transport of reactive nitrogen across the, or things moving from East Asia to the West Coast, we should think about them in summer just as much as we're thinking about them in spring. They occur every day, and the plumes are quite large. So also on the river that I've learned, and this is something that I don't think the model is getting quite right, is we've taken all these plumes of that we can observe from tests, or all these successful pan retrievals for each month in summer. So this is July 2008. And then I've colored them basically by whether they overlap an HMS smoke plume. So they're either in smoke, they're not in smoke, or we couldn't determine it. And what you can see over here is a summary of that for the month of July. So this is the percent of these retrievals that are in smoke from 2006 to 2009, and pretty much whether you use all or daytime retrievals, it doesn't matter. So somewhere between 15% and 35%, depending on the year, of this elevated pan is likely in smoke. So I think this is something that the model is not capturing, and this title was going to be too wrong, so make it right. That was my other funny joke title. So 2000, here is the successful test pan retrievals. So, and then they're gridded in a grid, and this is the model sampled at the time and location of the test pan retrievals and then averaged. And what you can see is that the model is missing quite a bit of pan over the western US and Canada, and has too much, which I won't talk about here, in the southeastern US. And what I'm showing here are examples that Juliet did of ramping up the emission ratio of NOx, and then rapidly converting that to pan. So you're basically emitting pan. So as you ramp that up, you don't produce this over here. And that's pretty clear. So what I do think is part of the solution, and I'm very, very excited about this, is what we've done is we've taken Maria Valmartin's a gridded estimate from MISER of biomass burning injection heights, and gridded that, matched that to the geochem heights. And then, so now we have a global map for the year 2008, which is of the same year that I'm still appear to be stuck in. But this is the fraction of emissions injected above the boundary layer by grid box. And what you can see is that these numbers are quite high for July over much of the northern latitudes and much of the Pacific Northwest, where you have really big fires that spread out across the whole US. And so here is an example of the improvement that you get. So this is, we should have probably done this in a log scale, and we just did this last week, and pan, the observations here in blue, a boundary layer injection simulation is in black, and injection above the boundary layer is in red. And so that's an example for, I think it's July 4th of the ArcTask campaign. So I'm really excited about that. So that's definitely a wrong. I think fires and pan is a wrong in the model, and I think this is this will finally make some improvements that I'll be happy with. And so the third one is a right. So this is in that simulation in 2008, I made some claim that fires in eastern Russia were really important as a source of pan, I think, to the global, northern global atmosphere in spring. And so here's some measurements of pan from tests over eastern Russia in April. And so this red tells you the number of attempted test retrievals. The black is the distribution of pan in this area here. And then the blue is the percent where pan was actually detected. So in 2008, there was more pan in the atmosphere, and that was anomalous compared to 2007 and 2009, for example, but not maybe anomalous if we had a longer time record. So in 2008, we're pretty sure that the elevated pan that was observed was due to fires. And in 2006, yes, there were fires, but it was also colder and there was more vertical mixing, so tests would have detected that more readily. So those are the new things that I've learned about the global distribution of pan, and there's more wrongs and rights sort of laid out in these papers of things that I think we're doing right and things that the satellite tells us maybe need a little bit more work.
Not at all. Okay. This helps to be some any shedding. Okay.
Sorry, that was easy answer.
Well, maybe to save time, we'll go ahead and let you escape that easily. Okay, so next up we have...
people, as it turns out. Look, two, right now.
All right, so next up we have Ginny Fisher.
All right, thanks. So I'm just going to jump right in. I'm going to be talking about alkyl nitrates, and this was set up pretty well by the talks in front of me. So I've been interested in these alkyl nitrates, which are molecules of the form RONO2, so they're a carbon backbone with a nitrate group stuck on the end. One example is the isoprene nitrates that Paul and Kelvin have been talking about. And these are formed in the atmosphere when you have emissions of VOCs, either from biogenic sources like isoprene, or from anthropogenic sources like oil and gas wells emitting ethane and propane. When you have these emissions in the vicinity of NOx emissions, they can combine in the atmosphere. The dominant pathway is just to re-release that NOx back to the atmosphere, which isn't very interesting, but there's a minor channel that forms this alkyl nitrate. And that's important from the perspective of the NOx budget because there are different possible fates for that alkyl nitrate. So I won't step through all of these except to say that only this red one at the top recycles the NOx. Everything else serves as a terminal NOx sink. And of course, just like pan, this can become a reservoir species that can be exported somewhere else, so your NOx release or your NOx sink happens elsewhere. So my goal recently has been trying to quantify the impact of forming these species on the NOx budget. And what I'm talking about today is going to be some of the smaller species that come mainly from these anthropogenic sources, although not exclusively, as I will say. And I got interested in this from a figure that looks something like this that I probably showed here 2 years ago when I was mostly interested in the isoprene and monoterpene nitrates, because I was looking at what was going on in the boundary layer, and you can see that they were really dominating the picture. But if you start to look in the free troposphere, oh, sorry, wrong way. If you start to look in the free troposphere, there's this wedge of brown stuff, and depending where you look, it can represent about 50% of the total alkyl nitrates seen in the observations in the free troposphere. And it's something that we typically haven't included in geochem. And the reason that this might be of interest is because unlike the isoprene and monoterpene nitrates, which are pretty reactive, these have long lifetimes of weeks to months, so they can be something that can be exported relatively far. Their main loss is through photolysis and oxidation, which is the pathway that recycles NOx. So it could be a missing source of NOx in the remote free troposphere that we haven't been including in the model. Luckily, these are easier to measure than the species that Paul was talking about, and we have about 20 years of historical aircraft data available to constrain this problem. So I've been putting these into geochem. I'm using our sort of hybridized post-seekers version that has all the biogenic chemistry in it. And the chemistry is actually a little bit simplified for these because they're not very sticky. Our emissions have been updated largely using the work coming out of Emily's group with a few additions. And there's just one thing I wanted to highlight about the chemistry for the chemistry working group, which is that the formation starts when you have a volatile organic compound, like ethane, that reacts with OH to form a peroxy radical, like ethyl peroxy, that can then go on to form the nitrate. The problem is that it's not actually that simple because the peroxy radicals have lots of different sources in the model. And this is just showing that there are all sorts of different chemical pathways that lead to those peroxy radicals, and that's not actually consistent with the nitrate observations, and we think we know the chemistry reasonably well there. So for my version of the model, I'm only making the ethyl peroxy radical from this ethane reaction. We have similar but different issues with the propyl nitrates, and this is maybe something we should talk about later. The other thing that needed to be added here is an ocean source, because these are known to have a flux from the ocean. The problem with this is that there are very few waterside measurements of alkyl nitrates, and so trying to force these with surface ocean concentrations is pretty difficult. The only data I've found so far is in the tropical Pacific, and so what I've got for now is seawater concentrations in the tropical Pacific, but this is still a problem, as I will show. After that, it goes through the same flux parameterization that we use for other species like acetone in the model. Okay, so without further ado, I'll just show a couple of comparisons of what we've got in the simulation so far. So these are all vertical profiles from aircraft. The aircraft data are in black, the model is in red. These are from source regions, so these are some different campaigns in recent years in the US. There are a few things that are going right and a few things that are going wrong, but for the most part, we're getting reasonable order of magnitude over source continents. If we start stepping into the remote areas, which is what I'm actually interested in here, in the North Pacific, relative to HIPPO and to older aircraft observations, we do a pretty good job with the ethyl and propyl nitrates. We're a little bit low for methyl, and I think that has to do with the yields, and that's something that's on my to-do list. But if we move into the South Pacific, we see pretty large underestimates, and that's in both the methyl and the ethyl nitrates. From the shape of the profiles, it's almost certainly an ocean source, and as you might recall, I didn't have anything in the ocean down there, so that's something that we need to add. But there's this really interesting feature, and it's been observed on multiple different aircraft campaigns, that the concentrations of methyl nitrate are actually a lot higher in the southern Pacific than they are in the northern Pacific, and we don't entirely understand why, so I'm hoping to talk to some oceanographers about how best to deal with these ocean-side concentrations. I do have other campaigns, but in the interest of time, I'm not going to show them. But what I will show you is sort of my simulation and data compilation so far. So this is not all of the observations that I've got, but many of them plotted atop. This is just a slice in the lower mid-troposphere as an example, so that you can see the relative concentrations of methyl, ethyl, and propyl here is largely dominated over the oceans by the methyl nitrate, over the continents by propyl nitrate. There are interesting things going on in the Arctic that I haven't looked at yet, but I'm quite curious about. And you can see that pretty big bias in the methyl nitrate in the South Pacific. So this is still a work in progress, but I still wanted to go back and look at my original question, which is what does this do to the NOx budget? Because although the simulation isn't perfect, we're going from a base simulation where we have none of these things to a simulation where we have at least some. And these are the percent changes in the NOx budget globally, annual mean. These are on a scale of -5 to 5%, at just two different places in the free troposphere. So the main impact is coming from this new source from the ocean. So although I was mostly interested in the export question, actually the ocean source ends up being most important. And that's somewhere between a 5 and 10% change on an annual mean basis with some interesting spatial variability. One thing that I wasn't really expecting and that surprised me a little bit is it's a little hard to see here, but there are actually decreases in the NOx in the export regions. And if you recall, what I was expecting is that you form these nitrates over the continents where you have the sources, you export them, and then they photolyze or oxidize, and you get extra NOx. But we see the opposite. And in the model, at least, that's reflecting competition between the alkyl nitrates and PAN. So there's a competition for the precursors and the NOx radicals. That means we're getting a suppression of PAN formation that can be on the order of 10%, and I haven't talked to Emily yet about whether that's good or bad or right or wrong. And that leads to a sort of pretty small and mixed impact on the ozone because the extra NOx from the alkyl nitrates is counteracting the reduction in NOx from the PAN. So we see changes that are order of magnitude 2%, although there are still some underestimates in the alkyl nitrates. So I will leave it there and answer any questions. Thank you. Thank you.
Do you see any difference on OH?
I haven't looked at the OH yet. Sorry.
We probably have time for one more.
So, this large source of methyl nitrate in the Southern Ocean, would that be a big source of NOx? Would that change then our understanding of the chemistry of that region?
I think it would be a big source of NOx because the NOx is very low there. And I think, if I can't find a good way to do this directly from the ocean, the other option is to try to infer it from the aircraft observations. But yeah, I think it's going to have an impact. The problem is we don't have lots of other data to constrain that impact, so I don't really know whether we have a problem in the Southern Ocean, whether we're fixing a problem or creating a problem, basically.
Thank you.
Thanks.
And our next speaker will be Jake.
Thank you. So now we'll switch and focus on the cold, dark biogenic-free winter. And I'd like to tell you about some of our analysis of the winter 2015 aircraft campaign, which took place over the Northeast US. And this was a large collaborative effort. And we were interested in 3 questions. First, understanding how well we understand emissions in the wintertime. Second, understanding some of the chemistry with some of the things that are particular to wintertime, in particular multi-phase and nocturnal processes. And finally, looking at secondary aerosol formation. And you can hear more about winter results from tomorrow from Ural Shai as a talk on aerosol formation. Jessica Haskins and Kelsey Larson have posters. So we conducted 13 flights between February and March 2015. Most of the flights were below 1 kilometer altitude, and half the flights were at night. We had a very rich chemical payload, in particular many species in the NOI family. We analyzed these observations with the nested grid half-degree geoschem model. We used the NEI 2011 emission inventory that we scaled to 2015 based on the SEMS observations in power plants and some of the EPA estimates for decreases in transportation. So let's first look at emissions. If we look at NOI profiles that were observed in black and the model in red, we see remarkably good agreement. So that gives us confidence in terms of the NOx emissions over the Northeast US in the wintertime. However, when we look at formaldehyde, here we see that the model is about a factor of 2 too low. And a lot of the formaldehyde observations show that the enhancements are highly correlated with CO, indicating that this formaldehyde is primary in origin, probably from transportation. And in order to match the observations, we had to increase the primary formaldehyde emissions by a factor of 5. And we think that one idea as to why that could be is that the NEI emission inventory might underestimate the cold starts VOC emissions, in particular formaldehyde emissions. Now this has important implications for the oxidant budget. When we included these enhanced formaldehyde emissions together with nitrile chloride chemistry, we see a large impact on HOX. HOX over the Northeast US increases by between 40 and 80%. And this in turn affects secondary aerosol formation, increasing sulfate and organic aerosol by 10 to 20%. Okay, so switching back to NOI, we get NOI right. Let's now look at the partitioning. So this is mostly for the bottom 1 kilometer over the US. The observations show that in terms of NOI, most of it, 70% is in the form of NOx. And the rest is divided among nitric acid, N2O5, organic nitrates, and nitrile chloride. It's not on here. Yeah. One big problem that we see compared to geoschem is that geoschem overestimates nitric acid by about a factor of 4. Now, this is not a new problem. It's been around for a long time. Lin Zhang and Colette have shown that during winter, nitric acid is too high. With the winter observations, we can focus a bit more on what's happening. Now we'll look at the nighttime NOZ, so NOI minus NOx. And now we can see that, yes, indeed, nitric acid is very high, but also that N2O5 is a factor of 4 lower compared to observation. So that's a clear indication that the gamma N2O5 is too low. In this simulation, we used the formulation that was implemented by Matt Evans. It's a function of aerosol type, relative humidity, and temperature, with a gamma of about 0.02. Since then, there have been a number of measurements that have shown that gamma N2O5 is inhibited by nitrate and also by organics. So we've updated the gamma N2O5 formulation to the observations by Tim Bertram and Joel Thornton. And that's a function of liquid water content, nitrate, and particulate chloride. We've also used the measurements by Badger et al. On humic acid for organic aerosol, much lower gamma. Also included the ClNO2 yield. The new gamma is lower over continents, and that's mostly the nitrate and organic effect. It's below 0.01, and then increases over the ocean. So a lot of variability. And here's the yield, low yield over the continents, little chloride available, but much higher over the ocean. Now this gamma helped quite a bit in terms of nitric acid, but not enough. So we looked, so here's the old simulation for a total nitrate. Here's the new simulation with the new gamma. We also looked at dry deposition, sort of the child left behind in terms of processes in geochem. So we noticed that many of the dry deposition velocities in geochem during winter, when surface temperatures were very cold, were extremely low. And we traced that to this exponential temperature dependence in Wesley, that's in geochem, that basically had an exponential increase of the surface resistance at cold temperatures. This is not very realistic and led to much too low dry deposition velocities. So for nitric acid, we set the surface resistance to 0, which is more consistent with observations. And for other species, we limited this temperature increase in the surface resistance to a factor of 2, which also increased, for example, the dry deposition of ozone. It helped for ozone as well, reduced our bias, and greatly helped for nitric acid. So now with these updated simulation, we have a much better representation of the observations in terms of the partitioning of N2O5 and nitric acid. So overall, if we look at what this means for the NOx budget and NOx export, we find that during winter, the NOx lifetime is actually fairly long, on the order of a day or a bit longer than a day. And this whole chemistry is fairly slow. And it's dominated by formation of nitric acid, in particular on aerosols. And then about half of the NOx that's emitted gets exported. And a lot of it is in the form of NOx that hasn't had a chance to react. And then the rest, about 40%, in the form of nitric acid with small contributions from organic nitrates and ClNO2. And I'll stop with that. Thanks.
We have time for a couple questions.
So did you compare the boundary layer height in geochem with observations? Did you see anything?
It looked right. Looking at vertical profiles of temperature, relative humidity, and estimates of boundary layer height, I think the winter time, it's reasonable.
So how high is the boundary in winter? I was curious.
So over land, about a kilometer or so or lower, and over the ocean a bit deeper. But there's always the residual mixed layer that had a lot of pollution. We had no problem finding pollution. Yeah.
If you have cold start contribution to something like formaldehyde, wouldn't you also have a contribution to increased organic aerosol, and as a result contribute to uptake of N2O5 from a cold start cause?
I do not know. It's not something I've thought about, and I don't know how catalysts react, function under very cold conditions, and which species are emitted more preferentially. Yeah, something to look at.
Last one more.
I was just wondering if do you have specific evidence that's leading you to think about cold start emissions as opposed to like wood burning or something like that with a formaldehyde or other chemical tracers that could kind of point in a specific direction?
We looked at CO. CO is maybe a little bit too low, but not. There's no huge underestimates. I don't know what other. I think the organic aerosols, for example, we reproduce more or less correctly. Yeah. But trying to figure out the cause for this would be interesting.
And next up, the greatest co-chair of all time.
What do you say after that? Okay, so the work I'm going to talk about has come from Johann Schmidt and Thomas Sherwin. They can't be here, but they're the guys who've done all the work for this, so I feel a little bit like a fraud talking about this. Johann is back in Copenhagen after being at Harvard, and Thomas did his PhD with me and is currently locked in the cellar under our building writing papers. But these guys have been quite productive, so over the last 2 years, they've written a series of papers about halogen chemistry. So most of the stuff we've heard so far has been about hydrogen, oxygen, nitrogen, and sulfur. So there's 4 elements. We're adding 3 more elements into sort of geochem. So if you're a chemist, that's quite exciting. You know, boron will come next. But I don't have much time, so what I'm going to do is quickly run through the results of the halogen simulation on various things that might be interesting to people. So when we switch on our chlorine, our bromine, and our iodine work, we end up with ozone global burdens dropping by about 19%. Locally, that can be up to about 12 ppb. The OH drops by about 8%. Locally, that can be a 20% drop in your OH. That leads to a 10% increase in your methane lifetime. We get 2% of the methane being lost through chlorine chemistry, but we get about 26% of our ethane being lost by chlorine chemistry. We have a new source of aerosol in the model from iodine, and in really remote regions that can be relatively important. The ozone, tropospheric ozone radiative forcing drops by about 1/4 because of halogen chemistry. And this can have, as well as these global impacts, this can have large regional impacts. So if I run out of time, you were interested in this, come and talk to me about these things. Okay, so we've got now in the model a representation of halogen chemistry. We have emissions of biogenics out of the oceans, out of the land by human activity. We have emissions of iodine compounds out of the ocean through an inorganic route. This leads to the production of halogen atoms and then a whole explosion of halogen chemistry. The difficult thing about a lot of this chemistry is that heterogeneous processes are absolutely central to all of this. And so we have a whole range of heterogeneous processes occurring on sea salt or on sulfate aerosol, which leads to a processing of this chemistry. We have a flux of halogens coming down from the stratosphere, and this is essentially the old CFCs and the old bromocarbon. You know, what goes up must come down. The stuff that caused all the problems in the stratosphere has to come back into the troposphere. And then we've got deposition. What we don't have in there at the moment is any polar-specific processes, so anything stuff occurring on snow. And this is all now in geochem, and Thomas is putting this all into version 11. Okay, so if we kind of run through just the sort of take-home messages, what we've got here is the surface ozone and the column, tropospheric column ozone, both as an absolute and a fractional kind of change in concentration. So what we can see are relatively large changes if we focus on the fractional changes. Over the remote tropical Pacific, over the Indian Ocean, you can see a sort of 36% reduction in surface ozone because of the halogens. Similarly, we can see relatively large changes in the tropospheric column, and overall this is about a 20% drop in the ozone burden. If we look at something like the processes which are losing ozone in the atmosphere, what we've got on the left-hand side are your classic HOX and OX cycles. On the right-hand side, the halogen cycles. So at the surface, about 30% of the ozone is being removed by these halogen cycles. In the upper troposphere, about 30%. Chlorine doesn't really play any role in the ozone destruction. And at the surface, it's mainly a story involving iodine. Higher up through the atmosphere, it becomes more balanced between iodine and bromine. If we look at OH, overall, the OH concentration drops with the inclusion of the halogens by about 8.5%. So our kind of global mean OH concentration goes from about 1.4 times 10 to the 6 to about 1.3 times 10 to the 6. The balance, the different halogens have different tendencies towards changing the OH. So iodine tends to decrease the OH concentration, bromine tends to increase the OH concentration, bromine tends to recycle HO2 into OH faster, iodine tends to drop the production faster. So our methane lifetime, without any halogens, which was about 7.47 years, with the halogens, the methane lifetime to OH with the halogens becomes 8.28 years, but that shortens slightly because we have a new sink which comes in from chlorine chemistry. If we look at the oxidation of different VOCs, This is the oxidation of some of the VOCs in Geoschem. The green bar shows the fraction that's being oxidized by OH, and the red is the fraction that's coming from the chlorine. We get about 2% of the methane being oxidized by chlorine, but we get up to about 26% of the ethane being oxidized by chlorine, and then it kind of drops off again as the carbon number increases. Bromine oxidation isn't particularly significant for the VOCs. Higher iodine compounds, so I202, I203, I204, I205, we think can disappear onto aerosol to make iodine aerosol. This is a map of the iodine aerosol mass concentration. And if you compare it to the sulfate aerosol in some regions, it starts in places which have got very low DMS emissions, the iodine can start picking up as being a reasonably significant amount of aerosol. If we run the model in a sort of guess at what the pre-industrial looked like and in the present day, if we don't have any halogens, we get an ozone radiative forcing of about 0.43 watts per square meter, which is pretty consistent with the last IPCC. But if we do run with the halogens, that number drops significantly. So that drops now down to 0.366. So overall, the inclusion of halogens reduces the ozone radiative forcing by about 25%. And the reasons for that are, in the present day, there's a larger flux of halogens from the stratosphere. In the present day, the source of halogens, the source of iodine from the ocean increases because that depends upon the ozone concentration over the ocean. And so we're ejecting more iodine into the atmosphere in the present day than we were in the past because there's more ozone. And we've increased the tropospheric bromocarbons in the present day. So overall, this gives us a reduction in the amount of the increase in the ozone reduces because there's more halogens in the present day than there are in the past. If we run the model, the regional configuration of the model over Europe, so we've run the model with halogen chemistry in the domain, halogen chemistry not in the domain, halogen chemistry in the boundary conditions, and halogen chemistry not in the boundary conditions, and then looked at the overall impact. What you've got on the top left there is the net change between running with halogens and without halogens in the domain. And so you get reductions, say, of the order of about 40% in the Mediterranean and about sort of 20-30% in Northern Europe. And that's made up of a combination of a change in the background ozone coming into the region and increased halogen chemistry or the occurrence of significant amounts of halogen chemistry in the Mediterranean. And so overall that leads to some relatively large drops in the ozone concentration. If we compare that to the UK air quality monitoring sites, the standard version of the model is in red. The green is the version of the model if we include the halogen chemistry, and the blue is the observational network in the UK. And so we remove the bias that was in the model by introducing the halogens. And if we start looking at so this is the cumulative probability distributions for the simulations without any halogens, with halogens just occurring locally, and halogens occurring locally and in the global domain. We end up getting some reasonably large changes in the probabilities of getting ozone in some policy-relevant kind of parts of the domain. Okay, so we get back to the main conclusions, which are essentially that the new halogen scheme has some fairly large impacts on the chemistry of the atmosphere. We've done quite a lot of work of running through some of the implications of this, but this is the first step and the first stage of doing this. There's a lot more work that needs to be going out to look at the chemistry and thinking about whether the chemistry is right or wrong. And hopefully this will all be coming to a model near you soon in version 11.2, and that's what Thomas is doing at the moment, is trying to integrate all of these updates into the new version of the model. Thank you very much.
We have time for one.
I'm a little puzzled by your radiative forcing 25% drop. Half of that is coming because of the stratospheric ozone.
No, half of it becoming of the flux of stratospheric halogens.
Stratospheric halogens.
What happened to NOx?
I thought you might ask that question. So NOx in general goes down because of nitrate hydrolysis,
And that's one part of the story about what's going on, is there's less ozone being made because there's less NOx, but a large part of the story is because of the catalytic destruction of ozone in the classic solar cycles. And actually, there are some quite large changes in NOx in some regions, and one of the things we want to do is see, is that realistic?
Next up, we have Eloise from University of Birmingham.
Yeah, it's there on top. Yeah. I'm not going to use it.
They can't hear in the other room.
Okay. Oh, sure. So I'm going to talk to you about these two new OMI-NO2 upper tropospheric products that I'm using to try and understand NOx dynamics by combining it with geoschem. The reason we care about upper tropospheric NOx is because it has impacts on ozone production, where ozone is a very powerful greenhouse gas. Just a very simple description of what these products involve. The typical approach to get total NO2 columns is to look at the solar backscattered radiation, where this radiation reflects off the Earth's surface. In this case, we're taking advantage of clouds within different portions of the troposphere, and we use this as our reflective surface. So we can get information now about a partial NO2 column. We can also take advantage of differences between clouds, and if we subtract the difference between these two partial columns, we can start to get vertical information about NO2. This is just giving you some idea of the spatial distribution of these two products that I'm making use of. So on the left we have KNMI, and that's for the year 2006. And then on the right we have NASA, and it's a multi-year product for 2005 to 2007. I'm just showing two seasonal means here. And there's a lot of differences in the steps taken to retrieve these two products, but the largest difference that kind of stands out in their spatial distribution is that NASA makes use of these very optically thick clouds to look at these NO2 scenes, and so you see less observations in the NASA product. The other notable differences is the calculation of the air mass factor. So in the KNMI product, they make use of an air mass factor to convert the slant column to the true vertical column that takes into account not only the viewing geometry along the viewing path, but also the absorption and scattering of radiation by aerosols and also trace gases. In the NASA product, they're just taking use of, or just taking into account the geometry along the viewing path. I'm showing the averages for the observations that are available within these seasons, but just to note that when you look at co-located observations, I find that the KNMI product is typically about a 30% lower than the NASA product. So in order to evaluate which product to progress with to convert to geoschem, I make use of aircraft observations from the NASA DC-8 aircraft that gives information where these satellite observations are seeing upper tropospheric NO2, so around 380 or 350 hectopascals, depending on which product I'm looking at. There's also two different instruments that observe this NO2, and so I've split the panels up into these two different instruments. On the left is the laser-induced fluorescence instrument, so the aircraft observations are the circles, and then on the right, the chemiluminescence instrument. There are also different campaigns, so they don't all reflect the same spatial distribution where these instruments are available. In the background is the satellite product. On the top is the NASA product. On the bottom is the KNMI product. And at least on a regional mean, the NASA product is more consistent with the aircraft observations, whereas the KNMI product shows that it's systematically lower than the aircraft observations. If I look at spatial correlations, I actually find that both products have a weak correlation with these aircraft observations. So really I'm guided by the regional mean in progressing with comparing to geoschem. So I make use of the NASA product to look at the spatial discrepancies that I see between the model and the observations to try and evaluate what we do and don't understand about upper tropospheric NOx. And so where we see blue, the model is low. Where we see red, the model is high relative to this NASA product. I've highlighted some spatial discrepancies that show up. In the northern mid-latitudes in winter, the model's lower than the observations, and also over tropical continents, so in Africa and South America, the model tends to be too high. So the first thing I looked at to evaluate against these observations is what could be the contribution to uncertainties in chemistry in the upper troposphere. And there's a lot of discussion in this in the literature, and in this slide I'm just highlighting the three reactions that show up as having large discrepancies and in what direction there are in the model. So N2O5 uptake is too fast in the model, NO2 reaction with OH is too fast, and then the NO plus ozone going to NO2, which changes the distribution of the NOx species, is too slow.
When I update this in the model, rerun it, I find that the discrepancies persist. In fact, in some cases, they're too high. Well, they worsen where it's too high because you increase the abundance of NO2. The other aspect that I looked at is lightning NOx as well. So in the NOx parameterization in the model, we estimate the lightning NOx flashes and then redistribute them spatially based on a climatology from satellite observations. And so the first thing I looked at is to what extent interannual variability could contribute to the discrepancies that we're seeing. So when I updated the model with interannual variability, looked at these discrepancies, I found that it didn't address any of them. So the next thing that I looked at is another component in the lightning NOx parameterization that we have in the model, and that's using the single value to represent the NOx production per flash. So in the model, we use this 260 moles of NOx per flash, and so I estimated what the spatial distribution could be if I scaled this 260 moles of NOx per flash by the discrepancy that we see between the NASA and NASA product and Geoschem to try and get some spatial information about this NOx production per flash. I find that in the spatial distribution, the moles of NOx per flash tend to be higher over the oceans than they are over land, and this is consistent with a new product that was reported in the literature on the actual properties of lightning flashes. So this report includes properties like the flash footprint or the extent of the flashes, the intensity of the flashes, and also the duration. And just for illustrative purposes, I'm just showing the footprint here, showing that there's a similar spatial distribution, so higher over the oceans, lower over the continents. It's still speculative as to what's leading to the spatial distribution. One proposed reason for this is that over the oceans you tend to have more cloud-to-ground flashes than intercloud flashes. These tend to be more intense and maybe leading to the production of more NOx. When I compare the only derived NOx production per flash to the lightning footprint as an example, I find that there's this linear relationship between the two. This relationship also exists if I plot it against lightning intensity or lightning duration, but the most robust linear relationship that I'm seeing is with this footprint. And so I think what's encouraging about this plot that I'm showing here is that perhaps now we can move towards something more mechanistic in representing this moles of NOx per flash rate, rather than using this as our kind of giant lever in the model where if we see that upper tropospheric ozone is wrong, what can we do? Well, we scale lightning. And so hopefully I can relate this linear relationship that I'm seeing to something physical in the meteorology in the model and provide us with something more mechanistic in terms of NOx production from lightning. I'm just going to leave my summary and also just some points and some future work that I'm going to be doing for this, and I'm happy to take any questions.
We have time for several.
Could any of your model measurement discrepancies be explained by the light path within the cloud that could be co-located with NOx within the cloud?
Yeah, so the KNMI product did try to correct for this. They made use of the TM4, TM5 model to try and make a correction for representative errors. I don't know if that's what's leading to some of the discrepancies that I'm seeing between KNMI and NASA product. In fact, when I actually played around with including this error correction and not including the error correction, it doesn't make a huge difference to the final product.
I think you deserve one more question.
All right. I was just wondering, so if I remember right, ski marking for a while was doing limb observations, right? So is there any data to be had, constraints to be had there on this problem?
I'm not sure. I don't know if anyone's looked at a Skiamaki upper tropospheric NO2 product. I don't know if anyone can comment on that. But it does coincide in terms of years, so it could be another piece of information to draw in.
Next we have Sarah Safi.
I changed the title of my slide because I just realized 2 days ago that I had the wrong title for it. But that's okay because it is based on the title that you have in your program. So as a general motivation for my work, I've been doing this work for 2 years now at MIT with Colette. And recently we've published a paper in JRL only last week that had a budget for reactive organic carbon, which is the sum of non-methyl volatile organic compounds and organic aerosol, which will have an effect on the climate, OH radical, ozone, and aerosol formation. I expanded the chemistry in geochem by including new emissions. I included chemistry, made the chemistry for monoterpenes and aromatics online. I expanded the wet and dry deposition scheme, and all of this was done while ensuring carbon closure in all of the chemical mechanism in geochem. So go through this budget. The reactive organic carbon will be dominated by, the sources for reactive organic carbon are either from methane oxidation or from direct emissions, and the sinks will be either physical sinks, wet and dry deposition, or chemical sinks, and that will be oxidation to CO and CO2. What I want to highlight in this budget is these two red numbers, and that you can see that the wet deposition, any changes in the wet deposition will have a direct effect on the CO2 produced chemically from reactive organic carbon, and that's the motivation for this study, because it will have a direct impact on the life cycle, and it will constrain this rock in the atmosphere. So in order to understand the dissolved organic carbon, which I'm going to talk about in this slide, we need to understand on what it depends, and it will depend on rain, and it will depend on the availability of soluble tracers, organic tracers in the atmosphere. And this will give us the distribution for dissolved organic carbon that you see here. I want to highlight, for example, that in winter, that's December, January, February, you can see how over high latitudes we have very low dissolved organic carbon. That's why, because it's dissolved in rain, and this is where you have snow. And then in summer, on the other hand, over the northern mid-latitude, you can see how it correlates with where we have high reactive organic carbon in the atmosphere. So the first thing that I've done is to compare with observation, and this is based on a compilation study that was presented in the reference you see here, and she compiled 30-year record of dissolved organic carbon. And you can see on the plot the dissolved organic carbon from geochem as it is simulated, and above that, the 30-year record. So I'm comparing 2010 with all of the samples of dissolved organic carbon measured, and first thing you notice is that there aren't many of them. So especially over the ocean, for example, over remote areas, we have really a scarcity of measurements, which makes this study interesting. And the second thing that is really interesting is that we have a surprisingly good agreement. Actually, the correlation coefficient is 0.67, and geochem tend to underestimate the observation, which we would expect. Now, given this, that what I present here, it will be interesting to use geochem to derive something from geochem that we can use, that we can measure, for example, with analytical techniques that can help bridge the gap between observation and modeling. And the average carbon oxidation state, that is defined, as you can see, is a metric, and it's directly proportional to O, so it will depend on the oxidation state of the molecule that we have, and will increase with oxidation. It was introduced by Jesse Kroll in his paper, and you can see here on the x-axis we have the number of carbon atoms that an organic molecule might have, and then on the y-axis is the average carbon oxidation state calculated from this formula, and you can see how eventually all the organics in the atmosphere will oxidize to CO2. I did the same, but I did it with geochem, considering that we know the chemical composition of organics in geochem, and I added one dimension to this plot, which is I weighted by the concentration, the tropospheric concentration, and what you can see first is that we have a high cluster towards the low carbon number, and that's because in geochem we tend to lump species together. And then second, you can see what dominates reactive organic carbon in the atmosphere, and that's acetone, all the alkanes, isoprene, and then some of the semi-volatiles. This is in the atmosphere, so we can do the same thing in rainwater. And this is what we get. Again, here what will appear is the soluble organic tracers. So you can see it's dominated by primary OA, formaldehyde. We have all the isoprene oxidation products. We also have the semi-volatiles. if you notice, if you take, and this is the zero line, and we can notice is that all the reactive organic species are mostly below the zero line, whereas in dissolved form they're slightly higher, and that's because we have an increase of solubility upon oxidation. So this is a nice thing that we can see that this average carbon oxidation state is higher in dissolved form. So in order to investigate this more in detail, I plot the spatial distribution of the average carbon oxidation state globally, and it was tough to find the right color bar that can both show this. And you can see how this average carbon oxidation state in the atmosphere is much lower than it is in rainwater. And then in winter, we have this high latitudinal distribution in the atmosphere that you can see it's very low, and that's because rock in the atmosphere is dominated in winter by alkanes, which are very reduced. These alkanes are not soluble, so they won't appear on the panel of DOC. I want to also note that for DOC, we have this increased average carbon oxidation state off the coast, and that's because when the species will be transported, they will be oxidized and they will become more soluble, so they will appear on this DOC. So that's it. I will leave you with my conclusions, and I will take questions.
Got time for a couple questions.
So you have a huge flux of carbon going through the DOC. I mean, it competes with going to CO2.
Yeah.
And that's very surprising. I was wondering how much of that DOC goes through the organic aerosol versus gets scavenged as gas-phase species.
You mean the chemical?
Yeah. So, yeah, maybe that answers that. Your deposition flux, is it mostly as the organic aerosol?
I don't have the numbers here, but they're mostly in gas phase rather than in the aerosol. There's way more many volatile organic compounds in the atmosphere, at least in geoscam, than there is in the aerosol phase.
Oh.
Ginger?
So there are a lot of studies showing this missing oil reactivity, which means unmarried chemical compounds, organic compounds. Have you given
Yeah, so you can look at the paper. It's online since last week, and we actually have a whole section on OH reactivity, and we've shown how we have a big increase in OH reactivity, and we also looked at the OH reactivity at different regions in the world, and we show that it is now more consistent with observational constraints, with observations around the world.
So in your last slide, I think it was, you were talking about what was happening in winter, giving you very low ROC.
Yeah.
But you don't see that in winter in the southern hemisphere. Can you comment on why?
Yeah, I guess that largely depends on the emissions, and as I said, more anthropogenically related, and these are like the anthropogenic emissions like the alkanes, and these are the least oxidized, and we don't have that many in the southern hemisphere. So it's mostly anthropogenic.
Okay, one more round. Thank you. And our last talk of the session is from Luhu.
So I get too interested in tropospheric ozone since I was postdoc here, and I recently started an assistant professor position in Missoula, Montana. And well, GeoScam is a grassroots model, and because of this spirit, this community, user community, is growing so fast. And because of this spirit, GeoScam has been updated very frequently, as you can see from many talks already from here, particularly over the last 10 years. So those updates in GeoScam over the last 10 years tend to gradually lead to more active troposphere chemistry. And here I show those, for one of the most important species for troposphere chemistry, the ozone, on the plot for the troposphere ozone burden and also production rate. And the last time we had those global evaluation for geoscam is Lin Zhang's 2010 work. One thing I need to emphasize here for this plot is this plot the geoscam ozone budget for the with a benchmark output, which means those changes are mainly reflecting model advances, not a real atmosphere. Because those benchmarks are simulating exactly the same year, so they're supposed to be the same, but actually we see this increasing. And this is due to many of you in this audience and making this progress for us to updating those emissions, updating chemistry, and as you have heard those Caltech talks for the ice cream chemistry, and we'll have more changes in the future. And also updating the meteorological field, because thanks to the NASA GMO office providing us the most state-of-art data assimilation for meteorological field. And I didn't highlight the most recent study for the version 11, but the basic numbers is not changing dramatically. So one of the critical questions we ask, does this make sense for ozone simulation? And so in this study, we provide a very comprehensive evaluation for this model, use ozone sound, using satellite data, and also use mosaic aircraft data. And so one of the conclusions we make is leading to this very pretty figure. On the left is the OMI satellite data for the mid-tropospheric ozone, and the right is the geoscan. Basically, they're pretty identical, and which is really good news for us. And one of the conclusions we reached out is geoscan, this version, we are testing version 10.01, but basically version 11 will be similar, provide the best simulation of the global tropospheric ozone simulation over the history of our history. This is very important information. So I could provide the next 10 slides tell you how good the model is, but probably most of you don't care about that. So let me talk about what the current problem is. So geoscan right now have a very large negative bias compared to ozone sound, particularly at a high latitude. Here I select the North Polar region, but basically the same thing for the Southern Polar region, but not many people live in there, so probably not many people care about that. So, and all this color, this black is ozone sound observation, and different color reflecting the same model, but driving with a different meteorological field. And right now, the current standard version we have called GSFP in red, and right now it have a systematic bias in a high latitude. So how are we standing in terms of for the tropospheric ozone budget compared to other model? Here I compared those budget terms for the burden and chemical production and the stratospheric tropospheric exchange. And those 4 different bars reflecting a multimodal study starting from earlier 2000 year to most recent IPCC 5th assessment. And as you can see, most of the model can agree on the tropospheric ozone burden, roughly 320 teragram plus minus 20, and a very small narrow range. But those models provide pretty wide range for the production rate, which means those models can produce a similar tropospheric ozone burden, but totally for different reasons. This is actually one of the biggest uncertainty in tropospheric ozone study. And the model also have those trend of decreasing tropospheric exchange, decreasing since the beginning of 2000 year till recent year. And mostly, I think it's mostly reflecting because right now we have a better meteorological field. So how does geoscan stand here? This geoscan right now have the high end of the tropospheric burden compared to other model, and also have the one of the highest production rate compared to other model. But we have the lowest tropospheric exchange compared to other model right now. And let me tell you one thing is that we have some kind of observational constraint on these global numbers, but they're not quite helpful because they have their limitation, and they provide very large uncertainty range, basically covering all the range we have. Some of detailed budget, as we can see from here, is basically those pie chart is not changing dramatically right now, and still HO2 plus O2 are the biggest source for ozone production, but the tropospheric ozone right now is play a much less role in the whole source turn. But we think right now that the high latitude underestimating model is due to this, may have something to do with this STE flux is too low in the model now. On the think side, again, this pie chart is not changing dramatically, but we have the new players, the halogen chemistry. Right now, it's only 4% in this pie chart, and not too big. But as you heard from Matt Evans' talk earlier, when we have implementing new halogen chemistry, that basically is going to break the model, and it won't have those pretty pictures we have seen for ozone. And so another big issue is, which is something I was struggling for a while. So when I see those increasing trend for ozone budget, and I was pretty optimistic and say probably we can solve the long-term trend problem. And apparently that's not true. So on the left side is David Parrish paper published in 2014, basically showing those 3 climate models that cannot reproduce just the multi-decadal trend over the last 30 years. And those climate models are those models used to infer IPCC assessment report. And their model overestimated the current ozone and also cannot reproduce the trend. But this newest GSCAM model, they can produce the current trend, but not the current level of ozone, but not long-term trend. And I was struggling to figure out why. I think there's probably some reason to explain that. And this is showing for another two set of side, for the Central European surface side and also over California and Japan, basically reflecting the change of the cross-Pacific pollution change. And apparently right now we have a widespread model overestimating in 1980s, and also those trend is not captured. Typically, I think it has to do with something with those, right now we lack those emission information over time. But if it's simply just the emission trend is not right in the model, I think that's a much simple problem to solve. There's much more. As shown in this figure, again, those mountainside over Central Europe, but this is showing in winter time. This cross, this point showing if the model does not have those anthropogenic emission. So basically tell you we need to cut all the anthropogenic emission in 1980s to reproduce this observed trend, which tells us another long-term issue in the model is the model right now is overestimating the natural background source. It's way too high. And this, we already know that for a while because Loretta Mickley had a nice paper 15 years ago talking about the pre-industrial level model is way too high. But it's not that long ago. It's just 30 years ago, in the 1980s, we cannot even reproduce that level. Tell us that we definitely have much more work to do, particularly working on those remote area and background ozone background environment. So I will stop here. I think I have more questions than I can answer, and thank you very much for your attention.
We have time for maybe one question.
So you said at the high latitudes you see this underestimate of the ozone, which you think might reflect a weak stratotropic exchange. But it's primarily a high latitude southern hemisphere signal that you're seeing in terms of this underestimate, right?
It's also the same thing in the South Polar region.
Right. So what I'm wondering is to what extent this could be an issue with the vertical transport over Antarctica? Because the Antarctic region is sitting pretty high up in the atmosphere. So when you degrade the model resolution, you might not be getting the right vertical transport that's bringing ozone down from the stratosphere.
You may have
rather than being an issue with the stratosphere itself, it's actually maybe more a topography issue than going to higher resolution might better resolve the vertical transport in that region.
So you're talking about the vertical resolution or just the horizontal resolution?
Well, this horizontal resolution affecting the vertical transport in that region because of the effects of topography, which is different from the stratotropic effects that are linked to eddies that you expect to capture better when you go to higher resolution. But I'm wondering if to some extent what you're seeing here is just the topography and the fact that at 2 by 2.5 or 4 by 5, you're just not getting the right vertical structure of the transport over Antarctica. And that extends pretty far south, pretty far north, right, to like 60 degrees south. And you'll see this effect. So the whole Antarctic region is going to be influenced strongly by the topography and the high resolution or lower resolution simulation.
That's a really good point. I think we should talk offline.
All right. And in the few moments I have, I also wanted to mention that Mei Yun Lin had some slides that she shared at the Background Ozone Science Assessment panel in March that suggested that some of the mismatch between the parish results and the models might be explainable by the methodology of sampling. I don't know if you look at that.
I agree. I think it's partly is true, but that's one of the, I think most of the long-term trend study are mostly focused on since 1990, and only 20 years. And as you can see, the observation does not show too much of a trend. And so basically, if you do that with geoscan, we can agree that with observation too, because of the trend is not that much, and everything is growing with the uncertainty bar. But the biggest change is since 1980. Yeah, thanks.
All right, so that concludes the talks. We have poster introductions next. If the poster presenters could come up. You've got 30 seconds and one slide. You got to time it.
Yeah. No, it's automatically switched.
Oh, it is. Okay.
But we just need to.
You okay? Yeah, I'm good. Who's good? I don't know who's good. One second.
Have any figure. Should I up?
So let me just remind everybody that for the poster presentations, we're going to have one slide and a 30-second presentation of that slide by the poster presenter, and then the slide will automatically switch. So there's no running over time, and I hope you get to enjoy the posters in the atrium to get more information.
Start? Okay, thank you. I'm going to talk about the collaborative impact on key tropospheric continents and oceans. Cloud distribution, it have very good distributions, vary a lot between model to model. And here we use the satellite observation from C3M, it's called C3M dataset, to constrain the model cloud distributions. Here we scale the monthly mean model cloud depths to the C3M, and then look at the changes in watch. You will find that global mean watch changing by 4%. Okay. Airborne instrument can be testbed to improve retrieval algorithm for before geoscience satellite is launched. In my study, I retrieved format column concentration from two airborne instruments in two aircraft campaign, Discover AQ 2013 and Cross AQ in 2016. Yeah, please come by my poster if you are interested.
So it's been about a decade since the geoschem community looked at North American isoprene emissions using top-down constraints from satellites. So I'm readdressing that issue using the geoschem adjunct now at quarter-degree resolution with an updated isoprene chemistry mechanism that we're pretty sure gets formaldehyde right. Using Megan version 2.1 and bias-corrected OMI formaldehyde retrievals. And using this setup, I really think we can constrain isoprene emissions on the ecosystem level scale. So I look forward to seeing you at my poster.
Hello. I'm also looking at isoprene, hoping to improve isoprene emissions over Australia using formaldehyde from OMI and estimating the yield using geoschem. Yeah, you should come see my poster as well.
So another formaldehyde isoprene based one, this time looking over India. I've run the geoschem model at 0.25 by 0.3125 and also used OMI retrievals, and the model results have both been used for the AMFs and as a comparison to, and find interesting things about biogenic emissions of isoprene over India. Thank you.
Hi, I'm Sri Chaliagundal from University of Minnesota. Today I'm presenting quantifying VOC emissions over Indian subcontinent using OMI and GOM observations, using high resolution nested over Indian subcontinent. So we find large underestimate over the northern part of India. So please stop by my poster.
Hello everyone, my name is Hansen Tao from Peking University. We are using the satellite observation of formaldehyde and glycol to constrain Chinese enormous VOC emissions and evaluate the impacts on surface ozone simulation. And if you are interested in my work, welcome to poster number 7. Thank you.
Afternoon, everyone. I'm Xin Chen from University of Minnesota. Our work presents a regional VOC budget over North America from high-resolution geoscam. We evaluated model results with airborne observations and point out some of the challenging VOC with significant model bias. Poster number 8 welcomes to stop by.
My name is Will Porter. I'm a postdoc in the HEALED group at MIT. And at my poster tonight, I'll be presenting some results from 2 different attempts, one more condensed than the other, at integrating aromatics and monoterpenes into geochem gas phase chemistry, including impacts on sun-Deutsch reactivity, surface ozone, and computation time.
Trace emit VOCs, which will produce formaldehyde. And formaldehyde, according to EPA, has a really large cancer risks. And so if you are worrying about your hiking experience or you want to know about, the exact chance of getting cancer due to surface formaldehyde, please stop by my poster. And by the way, this is not Daniel.
My name is Gary Huang for Harvard-Smithsonian. We actually use 2 OMI products, OMI SAO and OMI MS, to model GFD-LAMS, sorry, not GeoChem, maybe I should not be here, and to study the response of ozone to anthropogenic emissions, fires, and meteorology. Thank you.
Thank you. Oh, okay. So hi, I'm Alicia from MIT. I'm a postdoc there, and I'm working with Bastien Sauvage from the Laboratoire d'Aérologie in France in order to trying to understand the MOI appears in the upper troposphere, and especially in the case of lightning NOx emissions. So we are here comparing observations from the MOSAIC program and also campaign like ICAT or DC3 with the geoscam, an improved version of the geoscam model with a lightning plume scheme. So please come to my poster if you want more details on that.
Recent aircraft observations from the Seekers aircraft campaign over the southeast U.S. in 2013 showed enhancements of NO2 in the upper troposphere and much lower NO to NO2 ratios that could be captured by geochem. We suggest that the low temperature kinetics of the NO plus ozone reaction rate could be responsible for this discrepancy, and increasing this reaction at cold temperatures has implications for global tropospheric chemistry and for our ability to use satellite NO2 observations to monitor surface NOx emissions.
Hi, Ken Cushion from Penn State. My research and poster looks at uncertainties in tropospheric oxidants like ozone, OH, and HO2 for 6 different NASA field campaigns. And so basically we try to attribute then the uncertainties back to specific model inputs like emissions, meteorology, or chemical kinetics. So come talk to me about model oxidants and what we can learn with thousands of model runs.
Okay, sorry, I'm wrong. Okay, 15. Okay, I'm not up to the. Yeah, I'm 15 or something. I'm up there. Sorry.
Yeah, we don't have one for you.
Okay, I just have a quick talk. So basically, I'm Liang Feng. I'm from University of Edinburgh. I'm just talk about my poster is about how to infer the Bourbon foam and the dibromomethane ocean fluxes from aircraft campaign. We know that Bourbon foam and the dibromomethane are the important source to the atmosphere, the bromines. So they have the significant contribution to the possible stratified ozone loss but the surface emission have a large uncertainty. We just use aircraft data to infer the surface fluxes. Sorry.
You guys Is no one up yet? Okay.
If we could give a round of applause for all of our great presenters. And one more round for all of our
All right, where are we at?
Oh, was
time.
here, yeah. All right, business.
All right, take your seat, stow your luggage. The plane is taking off. So this is the afternoon carbon gases session, and we're going to start with Kevin, who's going to start us off with talking about carbon cycle and climate variability.
All right, thank you for you guys who've pulled yourself away from afternoon coffee. I know you need it. I certainly do. So it's without question that, unless you work for the Cato Institute, that changes in the composition of the atmosphere from dumping archaic carbon is changing the planetary radiative balance and the trajectory of our climate. But it's not nearly as bad as it could be. In fact, the natural cycle takes up more than half of the carbon that's released through things like fossil fuel emissions, except for back in 2015. 2015 had the largest atmospheric growth rate since David Keeling started making those measurements back in the late 50s. And the question is why? Where did it come from? And what's the relationship, or what insight can we gain from this sort of forcing on what might happen in the future? To address that question, we're going to use something called the NASA Carbon Monitoring System Flux framework. And it's simply taking a lot of carbon observations, informing or being driven through a set of process-based models of fossil fuel, terrestrial, and oceanic exchange. These in turn drive atmospheric variability from geoschem. Those CO2 concentrations, CO concentrations, are confronted with new satellite observations, namely OCO2 and GOSAT. We then use either a 40 VAR or a LATKF framework to then infer posterior carbon fluxes, and then we try to understand, looking at these models, what that entails. The first thing to understand about 2015, particularly in the tropics, is how strong the variations actually were. So if you're looking at the precipitation in South America, for example, you can see that it's one of the lowest in the historic average. God help those individuals in tropical Africa. You can see the trend in temperature is going up and up over the last several years, compounding itself. And then in tropical Asia, this is the areas including Indonesia, you had both dry and warm temperatures. So what we're doing is we're going to take, if you think about a carbon flux at any given grid cell, you can think of it as the total flux, the net flux, is equal to the sum of all these different components: fossil fuel, oceans, biomass burning, net ecosystem production, which in turn can be broken down as to the difference between respiration and gross primary productivity, and the chemical source. Here is the different sources of information that we use to describe each element of these. So the OCO2 is used to constrain the total amount. MOPIT CO is used to constrain the biomass burning. We use GOSAT SIF to constrain the gross primary productivity, and then we use our other bottom-up models to constrain the other pieces. When you do that, this is looking at the tropics in the drivers of the atmospheric growth rate between 2015 and 2011. So we use 2011 as kind of a reference year. So if you look at those, first of all, if you look at these numbers, what you're looking at in here is the total flux. This is the inferred gross primary productivity. This is the contribution of fire, and this is the inferred respiration. If you sum up all the numbers, the tropics released about 2.4 gigatons more carbon into the atmosphere in 2015 relative to 2011. And the tropics, now the analysis is global, but we're focusing on the tropics. More than 3/4 of that total change, total global change of 3 gigatons is attributable to the tropics. And that accounts for about 88% of the total atmospheric growth rate change. Now the contributions of each of these regions, tropical South America, Africa, and Asia, contribute about the same amount, 0.9, 0.9, and 0.6. But the reasons why they contribute vary from each continent. So for example, if you take a look here, you can see that most of that net exchange is driven by reductions in primary productivity, gross primary productivity, between 2015 and 2011. Conversely, if you look over on the other side in Indonesia, you're seeing a change driven primarily by fires. Indeed, it was those fires that shut down a lot of airports, led to a lot of aerosol loading in that region. And then finally, in the tropics, you're seeing that that's driven primarily by respiration. 3 continents, 3 reasons for why the carbon changed the way it did. But I want to take a step further. If you take a look here, this is the changes in GPP-weighted precipitation, GPP-weighted temperature, and the number of dry months between 2015 and 2011. Now, what's remarkable is that look at the scales of these changes. The difference is larger than 2 sigma squared, so larger than the climatology, are dominated here and here in Asia. But then for temperature, you can see this tight strip, where it's extremely hot relative to its climatological mean. What are the consequences? If you condition the response, that is, you choose those grids for which you have extreme forcing, you get the following. So if you see in the shaded region, this is the areas where we have large precipitation differences, and in tropical South America, almost all of the differences in tropical South America are related to regions that had climatologically high precipitation deficits. If you look at, on the other hand, for Africa, just across this strip, that strip accounted for about half of the NB increase, while only representing 30% of the area. And finally, Asia, which is dominated by biomass burning, is quite different than what happened in 97-98, where biomass burning accounted for most of those changes. So this point brings up an important question. If we think about carbon-climate feedbacks, do carbon-climate feedbacks as an agent of change occur because of changes in the mean of high-frequency events, or the changes in frequency of low-frequency events, but high-impact events? That is it the extremes or the changes in the mean that are the driver? Thank you for your time.
We should have time for a question. Matt's itching his hand or asking a question? Okay, just checking. All right, we're going to switch the order here. Andy Jacobson is going to go first, and then Andrew will go after.
Do I speak into this?
I think so. It's not echoing.
Okay. Thank you. We're going to confuse things not only by changing the order, but we're putting 2 Andys from Colorado working on CO2 next to one another. We are both comparing Geoschem to TM5. We decided to change the order because I am dealing with a simpler story and a simpler tracer, and Andrew Hsu is going to follow up with a full CO2 explanation, which is more complex. I would like to, first of all, I grew up using TM5, and I have to say that learning to use Geoschem has been a delight. It has been wonderful to see all the online documentation, all the Geoschem support team, and all the support that we've gotten, and specifically Christoph Keller was instrumental in helping us implement passive tracers, because we're doing this entirely without chemistry in this model, and so we were able to spin that up rather quickly, and it's now a standard part of the version 11 code. I was able to write a diagnostics module to sample what we call OBSPAC. It's a way that NOAA has of packaging and distributing observations. It is something that is available, and we hope to get it into the code base and have it used by other people. So I work on Carbon Tracker. That is an operational CO2 reanalysis system. Every year we release a new revision of our flux estimates, and what is known about inversions is that is that it's an under-constrained problem. There aren't enough data to do the problem in a robust fashion, just constrain it directly by observations. Therefore, we are extremely sensitive to details of how the problem is set up. And one of those details is, of course, the assumed transport. Since the days of Transcom, people have thrown multiple transport models at this problem in order to get a handle on what the uncertainty is due just to the transport. And that is indeed what we're trying to do with Carbon Tracker, to have two operational models running the system. I want to tell you a story about sulfur hexafluoride. It's a compound which is used industrially in electrical switching equipment. It's a dielectric that leaks out. It has no significant sinks anywhere, and so it is merely increasing over time. And because it is leaking from electrical equipment, it is analogous to fossil fuel emissions. And so we use it as a way to evaluate transport. And unfortunately, it works only at the very longest time scales and over the largest spatial scales. This is a picture of how TM5 did with SF6 prior to a bug fix that we implemented. And you can see these are the dark filled circles are marine boundary layer sites, and there's a bias, obviously. There's too much SF6 retained in the northern hemisphere, and it took 10 years for the TM5 team to figure out what was going on. It turned out to be a problem re-implementing convection in the model. Once that bug fix or that convective transport fix was implemented, we had this revised sort of result. By the way, the peak at 30 north is very close to Los Angeles, so it's probably a local contamination source. But there's no significant interhemispheric gradient in this residual now. So you might be asking yourself, where does Geoschem lie on this? And that is going to be the next slide. But the significance of this change cannot be overstated. We have done, every year we update our analysis with new data, new priors, higher resolution transport, different inversion methodologies, so on and so forth. And never has there been as significant a revision to our flux estimates as the one caused by this transport fix. This caused a redistribution of something like 300 teragrams carbon just to the North American sink alone. And this is how Geoschem does. It's somewhere in between. It looks like south of 30 north, there's virtually no problem whatsoever, but there is some sort of tendency to retain SF6 in the northern temperate and Arctic latitudes. So this is, I'm just showing, this is Geoschem all by itself. This, by the way, is Mara 2. We're using version 11 of the code. It's the same resolution as what we're using in TM5, basically 2 by 2.5 for Geoschem and 2 by 3 for TM5. So this is not the first time Geoschem has simulated SF6, but it is the first time that a problem was highlighted. In 2011, there was a Transcom paper on methane, in which a simple interhemispheric gradient constraint consisting of Mauna Loa plus Barrow minus Cape Grim and the South Pole was developed. That's the figure on the left here. Geoschem did very well compared to observations, and so I was wondering if that was, has something changed. The story is that it has not changed, that this is an insufficient metric to actually understand the SF6 distribution in the atmosphere. So on the right is re-implementation of that same interhemispheric gradient, and the current version of Geoschem does just fine in that particular metric. There we go. So the other nice thing about the OBS pack we have for SF6 is that it has a series of aircraft profiling sites in it. And so these are time series from 4 different locations: Poker Flats, Alaska, Trinidad Head in California, Harvard Forest, and Cape May, New Jersey on the right. The interesting thing is that we're seeing a lot of yellow Down here, exiting the continent, the map here, by the way, is the SF6 emissions themselves. So it looks for all the world like there's just a lack of vertical ventilation of the boundary layer. I don't see any synoptic or seasonal variability with this, so it looks very much like a simple transport story. And so I will skip ahead to the conclusion slide. I evaluated mass conservation along the line here, and it's great in version 11. Sulfur hexafluoride, I think, has a potential of being a very significant constraint on large-scale transport in geochem, and I'd like to see more people using our OBSPAC data. So, thank you very much.
So you know, for SF6, there was the sort of Britt Stevens paper where they looked at the relationship between tropical and extratropical partitioning. Do you know if there's been any analysis to show that there's a correlation between your score in SF6 and the way you partition tropical and extratropical carbon?
That's exactly what the revision did in TM5 for us. It changed the North American sink, reduced it by 300 or 400 teragrams of carbon, and put it into the tropics. That's why we're bringing geochem into the picture. Yeah. Steve? Absolutely, and I didn't present that here, but we have them sampled from both models, and I haven't worked up that display yet. I don't. I'll get on that right away.
All right, take it away.
So Kevin did a great job of introducing CO2 and flux inversions. Andy came in and stole my punchline. So essentially, I'm going to wrap up sort of what those guys talked about. I'm going to take Andy's story in SF6 and sort of push it through CO2, essentially. So just a couple of things I'd like to touch on. The CO2 inversion problem and how the transport uncertainty sort of fits into it. And I have a forward run of geochem against TM5 with CO2 fluxes that we'll look at, and then try to look a little bit at how the bias in that transported signal feeds back to biased fluxes on the surface. So I'm going to move through this slide pretty fast. Everybody's seen a cost function before. We're trying to optimize CO2 surface flux using OCO2, mean column CO2. Basically, it's a balance between a prior constraint and an observational constraint on the right. You see how the transport operator actually has to map our fluxes through to observations, at which the difference between those is captured in the sigma matrix there. So the big thing to remember is if we have errors in transport, they propagate into that uncertainty matrix. If there's a bias, it even gets worse potentially than that. So the idea was how our inversions are affected by variations on that T operator, in particular with reference to the OCO2 flux inversions that a number of us are involved with. So this is sort of the big picture. So what we did here was we took geochem at 2 by 2.5 degrees. I used MERA 1 in this case, and TM5 with ERA interim. We ran the Carbon Tracker 2016 optimized fluxes forward, and basically what you're looking at here are zonal averages over time. Obviously, the huge thing that stands out is you have a seasonal bias between the two forward runs. The way to think about this for those of you that are not wrapped up in carbon necessarily, is that we have drawdown in the northern mid-latitudes coming in May, June, so forth. And then we have a deep signal drawdown CO2 that gets propagated essentially to the north. In this case, it's geochem minus TM5, so it's actually more depressed at higher latitudes in geochem than it is in TM5. And keep in note, it's about a ppm to ppm and a half range. That's to be compared to maybe an 8 to 10 ppm range in the annual seasonal cycle. So it's maybe 10 to 15% of what we expect. Just to back out, it's not
a really simple zonal picture. If you take each one of those slices and look at it in space, there is variability. I put a couple different months on the bottom and show that the differences do have spatial coherence sometimes. We have issues more over Boreal Asia, it seems like, and maybe less so over the United States. And these are mean biases down here. On the upper right, I show actually the standard deviation between the two, which would be some metric of how you might fold the difference in the observation back into that sigma matrix. So random error essentially is on the upper right-hand corner, whereas your biases are on the bottom. And notice the structure is a little bit different. We have some highlighting of Indonesia and temperate Asia, which I need to look at, which I think is an effect maybe of a diurnal cycle mixing, diurnal cycle of transport mixing with very strong CO2 fluxes, which generate some high frequency variability. So if you take that zonal plot I showed a couple slides ago and you just take a couple slices out of it for the month, you can look at it in vertical, and this is sort of what Andy was showing, very similar. On the right-hand side, you have geochem, basically wintertime and summertime, and you see pretty clearly that geochem traps more of the source signal, which is what happens in the wintertime, traps more of the sink signal in the summertime. So at this point, we don't know which one is correct. We just know that the mixing essentially is different, although Andy has some evidence, obviously, with SF6 that implies one direction, I think, more than another. If you difference these, you also, I don't show this, but there's actually pretty good variability in the vertical. So you're looking at 2 or 3 ppm variability in the vertical, so much stronger than you do when you actually just integrate through the column. So the idea then is if you take those biases out of that seasonal plot I showed and you grab for every month and latitude band, you grab a bias and you drop it into an observation like OCO2, and then you invert that whole thing, what do you get for an estimate of fluxes that corresponds to the bias in the transport? And what I show on the right is essentially what you get there. Most of the interesting features are in the northern hemisphere where most of the transport biases are. You'll notice if you slice it up latitudinally from about 50 north up and 50 north south, you'll find that basically the flux patterns are going to be inverted, which sort of matches the bias differences that you saw across that 50 north latitude swath. So what I'm very interested in doing now is taking a set of OCO2 flux inversions that a number of us in this room are working with. You see a few results here on the bottom. There's maybe 8, 9, 10 people participating in this. So Kevin gave an introduction to the JPL effort. There's a number of other people doing these OCO2 inversions. You see we have a wide range of flux estimates here for Boreal Asia and temperate North America over a couple-year stretch. So what we'd like to do is sort of investigate this uncertainty with respect to what we know potentially about biases in transport. So, and hopefully we can use that in combination with the priors and some other pieces of it, of the inversion problem, to tease out the differences and come up with a little bit more of a robust conclusion from the OCO2 flux problem. So in essence, that's where we're at. I've talked to a number of people here already about this potential transport issue and trapping in the northern hemisphere. I think I'm going to learn quite a bit from Andrea, and Karen Wu has a poster, which I'm excited to look at. So I'll take any questions. I haven't. Well, after talking to Andrea, the idea, like Karen Wu's poster said, is as you're going to higher resolution in the parent model, you're resolving convection more, so the parameterized fluxes are a smaller piece of it. So if you're averaging that up, you're not going to be fully grabbing all the convection. So I think what I'd like to do, I haven't made that comparison, but I'm assuming there's going to be a difference there, and I think re-diagnosing it is probably the way to play with, although I find it odd that TM5, which I'm comparing to, moved in exactly the opposite direction over the last 5 years, from re-diagnosing it to taking the parent model convective fluxes. So I think there's a little bit of work probably still to be done with this, but it's important for any long-lived gas. Yeah. I haven't looked at any other pieces. This was this was really just a forward comparison of the two models, so there was not really a truth thrown in there. So Andy with the SF6 brought observations into it, but at this point it was just a difference between the two, but there wasn't a tie-in necessarily. So there's a number of different sources of data and vertical we definitely should look at, I think. So it's going to be it's been a challenge for a long time, and I think it's one we're going to continue to work on.
Any other questions? Great. Otherwise, Dylan Jones is next.
Did someone walk off with the pointer? Oh, there it is. Okay, great, thanks. Okay, there's been a slight change in the title. I'm actually going to talk about some work that was done by Brendan Byrne, who's a graduate student in my group, who couldn't be here with us today. And Brendan was interested in understanding what can the observations of atmospheric CO2 tell us about the distribution of surface fluxes. So following on the themes of Andrew Shu's talk. Now, the motivation for our analysis was the fact that over the last decade or so, we've seen this significant expansion of the carbon observing system. We have the GOSAT instrument that was launched in 2009. We have OCO2 that was launched in 2014. In support of these missions, the Total Carbon Column Observing Network, TCON, was deployed, and that's been growing in time. We have GOSAT-2 that's being planned. There's an OCO3 that's being planned. China launched TANSAT last year. So we're seeing this really remarkable growth of the carbon observing system. And the surface network itself has also been expanding. But what's been really frustrating for us is that despite this expansion of the observing network, what we find is that inverse modeling studies that use these observations to try to infer regional sources and sinks of CO2 cannot produce robust flux estimates. We see large differences between the different inversions. And to some extent, that's due to the fact that there are model errors, as Andrew talked about before, but fundamentally, it's an underdetermined problem. And so Brendan and I were curious as to how sensitive are the observations to the surface fluxes? And that's the sort of thing we can do quite easily with the adjoint of GSChem. So we decided to use the GSChem adjoint to determine what are the differences between the observing systems in terms of their sensitivity to the surface fluxes of CO2. Okay. Now, to give you a sense of what the spatial distribution of the observations look like, the top panel here shows the observations distributed in space and time, so showing the data density from the surface network, aggregated for seasons, so SON is September, October, November, so fall, winter, spring, and summer. And the surface network here, data here coming from the NOAA prototype OBSPAC. Okay. And what you see is that the data are pretty concentrated in North America and to some extent in Europe. Fewer observations around over the other parts of the globe. The TCON network is less dense, but it's growing in time. That was designed specifically for validating the satellites, but we're realizing we can do some good science from the network, so we expect to see that expansion continued. This is the GOSAT observational coverage and OCO2, and you can see the significant increase in observational coverage as we go from GOSAT to OCO2. So what we decided to do is to sample the model at the observation locations and times. So we're not going to use real data. We're going to generate pseudo data from GSChem using this spatial and temporal distribution of the observations, and then use the adjoint to try to back out the sensitivity of these observations to the surface fluxes. Okay? So we're taking the adjoint, and if you have an observation at a particular point in space in the model, you can run the adjoint backward in time to determine what is the influence of the surface fluxes on that observation location and time. Okay. So you can produce a map of the influence functions, if you will, for a particular observation. So what we've done is we've aggregated all of the observations from each of the different observing systems as a function of season, so we create a sensitivity function or cost function that's the aggregate of all of these observations, and then we use the adjoint to get the sensitivity of those observations to the surface fluxes. So you produce an aggregated map of how a unit change in the surface fluxes in the model would influence the observations as aggregated here as a function of time.
Okay. So what I'm going to show you are maps of this sensitivity that tells you how each individual grid box would change the aggregated CO2 observations for the different observing systems, and we're looking at the sensitivity for the surface network, TCON, GOSAT, and OCO2. Okay. And again, these are not real observations. We're using the forward model to generate pseudo data. Okay. So that is what comes out of the adjoint analysis. The top panel here is showing the sensitivity for the surface network as a function of season. So for each, you can look at, if you were to look at one particular grid box, it would give you the sensitivity in ppm of CO2 per unit flux, in this case in kilograms per meter squared per day. So it's telling you how a unit change in the CO2 flux in any given grid box would influence the aggregated CO2 concentration in this sensitivity function for the different observing systems that are shown here. And you can see that for the surface network, the sensitivity is high across North America and Europe, but very little sensitivity in the southern hemisphere and the tropics. And as you go with the satellite and the GOSAT and OCO2, you can see increasing sensitivity, particularly in the tropics. OCO2 really dominates across the tropics. And in summer, OCO2 really gives you a strong constraint across Eurasia. If we look at the different modes of the instruments, for GOSAT, there's a nadir land mode and a glint ocean mode. You can see that the sensitivity for the two different observation types are comparable. But for OCO2, the ocean data just dominates compared to the land data. So if you're really going after the surface fluxes, the ocean glint data from OCO2 provide the greatest sensitivity to the surface fluxes in your analysis. So what does this mean for flux inversion? We did an Aussie where we took the pseudo data that we generated and fed them into an inversion analysis starting from an incorrect prior. So we scaled the fluxes down by 40% to generate a prior, and then we looked at how well we can retrieve the true fluxes using the different pseudo data for the 4 different observing systems. So where you see blue colors, that's about 0.6. That means you're really just getting back the prior. There's no sensitivity there, no information coming in from the data. And where you see red colors close to 1, you're retrieving the true fluxes. So for the surface network, you can see over the seasonal cycle, you're really pulling out the North American European fluxes fairly well. But you have very little sensitivity in the tropics and southern hemisphere. So when you compare 2 different inversion results with surface data across the tropics, you're really looking at prior information. And that was a point that Andrew made in his talk, that the differences between inversions is not just due to the inversion approaches or transport errors, but also the prior information that you feed into the analyses. For the satellite data, you can see that the greatest sensitivity is during the growing season in the boreal summer. Throughout the rest of the year, there's much less sensitivity. And that means, again, if you use satellite observations for an inversion and you try to compare observations from the results from 2 different inversion analyses, you have to ask yourself how much of the differences is really the prior differences versus actual information coming in from the analysis. So just to quickly summarize, since I'm out of time here, is that the satellite observations are giving us a better constraint on the tropical fluxes, but the greatest sensitivity is to the extratropical northern hemispheric fluxes during the growing season. They really aren't able to capture the seasonality of the fluxes in the extratropical northern hemisphere. The surface data, on the other hand, can do that, but they have very little sensitivity to the tropics and the southern hemisphere. And so, you know, the best we can do at the moment is to think about combining the two. It's not an either or. You really can't rely just on the surface network, nor can you rely just on the satellite data. You really have to combine the two, or think about how you will expand the observing network if you want to get better constraints from space so that you can capture that full seasonal cycle of CO2. Thank you.
So Dylan, if you bring up that last plot, you noted that the tropics is relatively insensitive, but there's some impressive spatial gradients in that sensitivity. You go down to OCO2 at the bottom. Look at the arc of deforestation in the Amazon. You crank up to about 1. And then in Africa, you do the same thing, sort of above South Africa. Can you explain why you have such a strong spatial gradient in the recovery in OCO2 in this approach?
I'm not quite sure I understand the question. If if you go back to the sensitivities here, let me see if I can go to full mode, full screen mode.
I'm just looking at the recovery. You see you get 1.
Good.
If you look at that recovery, you're getting 1.
Yeah. Mm-hmm.
But just downwind, it's not that. So you have a strong spatial gradient in that recovery.
Right.
I'm trying to understand why.
I suspect it has to do with this, the variability of the observations you're getting over the ocean. The ability to recover the fluxes, land fluxes with OCO2 data, in my opinion, is strongly influenced, as you can see here, by the ocean observations. It's not the land data that's driving the information. And you have a lot of ocean data, and in a real inversion, they're actually going to be more precise than than the land data. And so the question is, what's the variability of the ocean data, and how does that allow you to constrain the fluxes? So what you're, at that point, really sensitive to is transport. How is the transport affecting the land signal out over the ocean where you're picking it up with OCO2 data? So it's not as though most of the information is coming from observations right over the source or sink region. You're relying on transport to send that information out to the ocean where you have a tremendous amount of OCO2 data.
That'd be worthy for perturbation analysis.
Do we have time for one more?
We were a little bit ahead.
Oh, right. Go ahead.
Dylan, really interesting, because in the test that you do on the page following this, you perturb all your emissions uniformly. Then these signals that you're seeing, that sort of Kevin was talking about, might those then just be owing to the fact that you have peaks of prior emissions in particular locations? Because the relative peaks in your initial guess or your prior phase test will be the same as your pseudo observations. So I have a hard time sort of separating how you know what you're getting from your prior versus what you're getting from the observations, given that you still have that same structure of your prior as you do with your pseudo observations.
I'm still struggling with your question. I've been trying to follow.
Are you scaling or are you batting?
We're just scaling. We're just scaling the fluxes.
Your signal noise will be different.
Right.
Because the true emissions and the prior emissions have the same spatial structure relatively, then inversion sort of working better in this particular area might be because in that area you happen to have large emissions in your area.
Yes, true. But I guess the question I think Kevin was asking is why is it that what's driving the inability to... maybe we should take this up offline in the interest of time.
Maybe, good idea. Not a bad idea. All right, so Chris Holmes is up. I really like your title. Hopefully you would just now explain how this works. Coupled stratosphere tropospheric chemistry raises the methane global warming potential.
Do I need to say more? Where's the pointer? Is this it?
That's one, this is another one.
I'm using the wrong end. Okay, so I am going to try to show you that properly accounting for coupling between the troposphere and stratosphere increases the methane global warming potential. Now let me review what the global warming potential is. So methane, for each molecule of methane, there's a strong radiative forcing, but it's short-lived, so it decays away quickly. For CO2, each molecule has less radiative forcing, but it persists for a much longer period of time. The integrated radiative forcing, the area under these curves, is the total climate heating. And if we integrate over 100 years, each kilogram of methane has about the same total warming over that 100-year time horizon as 28 kilograms of CO2. Now we need to break down a little bit more where this methane warming comes from. So here's the greenhouse effect. Solar heating warms the surface. The surface emits infrared. Some of it is transmitted directly out to space, and some of it is absorbed by greenhouse gases and radiated back to the surface, the greenhouse effect. If we add a little bit more methane, that will capture a little bit more of the terrestrial infrared and radiate more down towards the surface. If that were all that methane did, that's the direct effect, the methane GWP would be 13.5. That's way less than the 28 conventional number that we'll get to. So there's more. Methane, when emitted into the atmosphere, sucks up some OH, leading to the methane perturbation living longer. If we account for that, then still less or more radiation is sent back towards Earth, and the methane GWP jumps up to about 19. But that's not where we end. Methane is a precursor of tropospheric ozone, and if we include that, the GWP is 25. And IPCC has also included that methane is a precursor of stratospheric water vapor. If we include that, the GWP now gets up to the conventional number of 28. But are these all of the indirect chemical effects of methane in the climate system? It's not. We need to include, in addition, methane is a precursor of stratospheric ozone, and when you have perturbations to stratospheric water vapor and stratospheric ozone, those are going to interact with each other through the Hawkes cycles. So if we account for all of these, in a paper from a few years ago, I had one model that had all of this chemistry in it, and it suggested the GWP was 32. Now, we highlighted that as like, here's an interesting thing, but it's only one model, so does this really hold up? Well, we didn't know at the time, but now with the UCX chemistry and geochem, we can answer this. But I want to add one further thing. If we include carbon cycle feedbacks, that adds 6. Regardless of whether you start at 28 or 32, you add 6 more for carbon cycle feedbacks. But the UCX chemistry and geochem gives us the ability to answer this question in a second model using a consistent framework. So I'm using the UCX chemical mechanism in version 11. It has a surface methane concentration, which I run in a base control simulation, and I also perturb it 5%. I include a few updates. I've included H2 chemistry so that I can follow the full cascade from methane down to water vapor. I also slightly changed the way that H2O is prescribed up to the tropopause, but in the stratosphere, the water vapor is entirely responding to chemistry and transport. It's not prescribed from geos as it is in the troposphere. I also have detailed diagnostics. So the model is in blue here for the total ozone column. It's 10 to 20 Dobson units higher than observations. A little less than 7% bias. Here is a time series from 2004 to 2010, from the South Pole to the North Pole. Model at the top and observations are very similar, but so we can see things better if we look at anomalies. And here we see a lot of encouraging things. For example, in the polar regions, the years with high and low polar stratospheric ozone loss correspond in the model and observations. If we look at the tropics, the QBO has about the right magnitude and period, but there seems to be a phase shift, which I don't have an explanation for, but it's an interesting discrepancy. So now let's look on to what happens to a methane perturbation. Here is ozone in the model, so ranging from under 100 parts per billion in the troposphere up to 5,000 in the stratosphere. When we add 5% methane throughout the domain, we have about a 1% increase in the troposphere, a little less than 1% in the upper troposphere, lower stratosphere, and about 0.1% in the stratosphere. So the message here is that methane emissions have a bigger impact on a ppb basis in the stratosphere than they do in the troposphere. On a percent basis, of course, they're larger in the troposphere. Why? Well, I can tell you that methane is a precursor of ozone in the troposphere and UTLS. In the upper stratosphere, what you have is methane suppressing the chlorine sink. The bottom line message, though, is that methane increases stratospheric ozone, no surprise there, but this has not been included in the methane GWP previously. So let's put it all together. These are two different simulations, the UCX model, a version of geochem on the left, and a troposphere-only SOA simulation on the right. The methane lifetime is just about the same in the two. Whether you look at the total lifetime or the OH lifetime, the feedback factor and the response of ozone to a methane perturbation are different, however. When you increase methane 5% in the troposphere-only model, you get 0.3 Dobson units response. When you give you the same amount of additional methane to the stratosphere and troposphere model, you get more ozone. Plus, the feedback factor goes up. When you convert this into, I had literature comparisons. Let's just say that the lifetime is still a bit too short. When we look at the GWP, now we have geochem with a GWP of 33 without accounting for carbon cycle feedbacks. The troposphere-only model is 28, very similar to the IPCC estimate based on the same mechanisms, but when we add in stratospheric coupling, the GWP jumps up to 33, add 6 more for carbon cycle feedbacks. We now have a methane GWP of about 39. So a big increase. So accounting for these interactions raises the methane GWP. Now we have 2 models that this is based on. That's still not enough for me. I'm working with Alex Archibald and Aman Sovda to add 2 more models. So we'll have a robust answer to this.
What are the carbon cycle feedbacks?
Well, in a general sense, it's just warming the surface and either increasing respiration or methane emissions from wetlands. It's all of the surface carbon cycle feedbacks. Yeah.
Is your radiative forcing computed at the top of the atmosphere or at the tropopause?
So in this case, Geoschem currently does not do radiative forcing for infrared active gases because we don't have a stratospheric temperature adjustment. I'm working to include that. For this work, I used pre-computed radiative forcing efficiencies that were calculated with Gunnar Mira and his widely used radiative forcing kernel.
The 2 other models that you're testing, do they have a substantially different treatment of, say, stratospheric tropospheric exchange or stratospheric chemistry to kind of test all the realms of possibility in a model?
They have almost totally independent heritages, so I have not compared them in a detailed way, but they certainly they range in complexities. I would say yes, they certainly sampled many of the different approaches to modeling these 2 systems.
So next up is Jared. Jared's title is not as exciting, but it's okay. Jared's my student. He's used to it. He's used to the humor. But anyway, Jared's method is very cool. So even if you're not interested in acetone, except maybe when you remove your nail polish, gentlemen, then you should think about the information that he's getting from this and whether it applies to your science questions.
Acetone is cool. I think so. All right, so I don't have to spend too much time with this group talking about why acetone matters, but I do want to give you sort of the overview. Back in 1995, Hanwant Singh et al. Found that acetone was a potentially major source of HOX in the upper troposphere, but that was relying on some older research on the quantum yields. So a reanalysis of the pressure-dependent quantum yields by Blitz et al. In 2004 and some modeling work by Arnold et al. The following year suggested that acetone HOX production was lower than previously believed. However, we have some more recent update to that literature. Neumeyer et al. Using the Karabic data set suggests that acetone HOX is a source, or acetone is a source of HOX somewhere on the order of 60 to 95% of that from ozone, which would suggest that it's actually, yeah, still important and still worth taking seriously, looking at the HOX budget. In the atmosphere right now, acetone is ubiquitous. There's a strong seasonality in the northern hemisphere. This is Geoschem output for the mid and upper troposphere, alongside some campaign data sets. And what you can see here is there's a very strong seasonality in that Siberia boreal forest area between that mid-October and November to April timeframe. Acetone itself is also abundant on the order of about 2 ppb over source regions and more like 200 ppt over the remote oceans. As treated in the model, there's 5 sources, 4 sinks. You've got 3 biogenic sources, terpenes, direct biogenic emission, and biomass burning, and then anthropogenic emissions and oxidation of isoalkanes. We've also got sinks to oxidation by OH and sinks to photolysis, as well as dry deposition and net ocean sink. So this is a fairly self-evident statement about model sensitivity analysis, but I bring it up to set up my metaphor here, which is the idea of a mixing board. So we can test multiple input factors at once and get more information than just how much does a single factor impact what the model does. We can look at how do different factors interact with one another. Now, to do this fully would require thousands, tens of thousands of model runs with every possible permutation. So instead we use something called the Morris method, wherein we utilize the setup of our experiment so that we get more information out of the total set of model runs than you would of doing each of them individually. So I used for this, for the research that became this paper, I used 88 simulations rather than something on the order of 10 to the 4 or 10 to the 5 you'd need for a Monte Carlo or variance-based analysis. So these are the settings that I used. We can talk more about that if you guys are interested after the fact about the Morris method. But here's what I was looking at. I was looking at 6 natural factors in the global acetone simulation. The yield of acetone from terpene oxidation, the emission of the biogenic terpenes from Megan, the direct acetone emissions from Megan, the acetone dry deposition, which is prescribed as a single value in the model, the oceanic acetone concentrations, which are also a single value in the model, and the acetone photolytic rate. And you can see all of the uncertainties I've assigned to these based on the literature. We can also talk more about that. This is what you get out when you do the Morris method sensitivity analysis. These are 2 different measures of factor importance. And they're purely qualitative, so the actual values don't matter, but the relationship of points to one another does. You have the absolute model sensitivity on the x-axis there, and then a term taking into account interactions between factors on the y-axis. And both of those are potentially markers of importance. So, globally speaking, biogenic emission of acetone is the most important of the 6 factors that I tested, followed by photolysis. And the factors related to monoterpene emissions are the least important. And that makes sense based on the scale of the emissions in question. This would be another way of looking at the kind of output that you can get from the Morris method analysis. This is the mid and upper troposphere and the sensitivity for each pixel in July. And again, this is the absolute sensitivity, the mu star, and the actual numbers don't matter, but the relationship between them does. So you can see here the model is most sensitive to photolysis in the mid to upper troposphere, which is precisely where it matters the most. So if we're not quite doing that photolysis rate right, it's going to really matter in that upper troposphere where acetone is important in the Hawks budget. The uncertainties in the biogenic emissions of acetone are most consequential in the tropics, as you can see here. And finally, now we're looking at the surface and the mid-troposphere, and you can see that ocean uncertainty is less important than the other factors, but it's less important over a really big area. And it turns out it matters quite a bit, especially in the subtropics and especially in winter. So all of this goes together to get to sort of the big take-home points, which is, 1, biogenic acetone is the most important thing that we should try to reduce uncertainty in. 2, without ocean exchange, the models won't get acetone right, especially in the southern hemisphere. 3, the model's really sensitive to photolysis where it matters. And 4, just sort of a more general thing about sensitivity analysis, a big range of uncertainty does not necessarily imply a big factor importance. So, happy to take any questions now, and love talk if anyone wants to talk about the Morris method afterwards, too. I've thought a bit about this. So it depends on how complicated you want to make it. The simplest way, so there's not a lot of data that we have on how much acetone there is in the ocean, but one of the simplest things we have a couple of these transects through the mid-Atlantic that go all the way from Britain down to Argentina, and you could kind of replicate that seasonal pattern and plug that into the model instead. And that would be really simple. Something a little more complicated would be to use the ocean model that we already have for like the ocean mercury simulation and sort of add acetone into that. And I think that's something that's really interesting, and we've talked about it a bit, but I just haven't gotten there yet.
So Jared, do you have a recommendation for how we should fix the acetone simulation?
Well, so I think so I've done a little bit of comparison between specifically the photolysis rates from Frappe and Seekers, and I actually think that now I chose a number that was a little too low for that acetone sensitivity. The numbers from Frappe and Seekers are something more like 2.5 to 3.5 times lower for our model, our photolysis in the model, than the photolysis rates that they got out of those campaigns. So I think that that's a place that we should really be looking for the first point. I know that given that I just said biogenics is even more important, but I think that this is a sort of low-hanging fruit that we can tackle.
Within the acetone photolysis, do you have a feel for whether it lies more in the temperature sensitivity or the quantum yield?
With the temperature sensitivity in the quantum yield, or the temperature?
Yeah, whether it's the sensitivity itself or whether we're doing something, whether we have a bigger error, like a more consistent error.
I don't know the answer to that, but I'm going to Orléans this summer to work with Abdul Wahid Malouki, so I should be able to give you a better answer after that.
There's some kind of discussion about the role of monoterpene oxidation as a source of acetone and the silver paper coming out. What's your thought on that? I know you mentioned that monoterpene is not important for acetone.
So I guess the question is, there's a new paper coming out that suggests that the monoterpene oxidation yield for acetone is more important than I'm making it. Well, I guess that's possible. My range for the specific oxidation yield was between 7 and 21%, and that's trying to take into account all of the monoterpenes that Megan puts out. I guess if that number were a lot higher, that percentage yield were a lot higher, it might be more important, but just generally speaking, monoterpenes are such a small source in the model compared to all these other factors that, I mean, maybe, but it doesn't seem as likely to me.
Thanks.
Thank you.
And then we have our, yes, we are our last, Nicholas is our last speaker of this session.
There is no.
There is. There's this one. Yeah, and that's the direction.
How do I switch? Yeah. Okay. Hi everybody. So today I'm going to present a new framework for high-dimensional source inversion, so to improve both the interpretation of the results and also the cost of the inversions. So a typical high-dimensional source inversion would be an update of a high-resolution bottom-up prior emission inventory using a bunch of data, such as satellite measurements, aircraft measurements. So you use a model and you are trying to find an emission inventory such as the model concentration better match with the observation. Now, the observation, the model concentration, and the prior inventory are not perfect, so you have to find a compromise. And what we do mathematically is that we minimize the cost function, which is the sum of the observation and prior departure weighted by their respective error statistics. And so in the high-dimensional world, typically we rely currently on iterative gradient-based algorithm in order to minimize this function, and we use for that an hadron model. So now we have many limitations currently with the system. So for instance, variational minimization are expensive. You need for each iteration one forward and one adjoint integration. And so sometimes you may need like 100 iterations or even more to get to the solution. And so often in practice it is stopped using some somehow arbitrary criteria sometimes. And the question is, how can we interpret rigorously what is the approximated solution, for instance? We need also better representation of the posterior information, such as posterior error, variances, and we may want to be able to, it would be nice to be able to do some posterior sampling to see the correlation in the solution, etc. Lastly, I'm going to also talk about the need for efficient algorithm to tune the prior and the observation error covariance matrix in the system, which are actually very arbitrarily prescribed right now and so highly uncertain. So how can we deal with those problems? So it turns out that those limitations can be addressed very efficiently, as soon as we solve the problem in the right subspace, in the right subspace. So the approach consists in looking at an optimal projection, and I will briefly explain what I mean by that. The optimal projection approach consists simply in solving the problem for just a small set of patterns, or emission patterns, for instance, that are most constrained by your observation. And the question is, how do you compute this subspace? And so a good mathematical object to measure the information content is a so-called prior precondition Hessian, represented here. So it's a geometric representation of it. It looks like a cucumber. It's like a quadratic form. And so to find the most constrained space, we need to find the principal axis of this quadratic form. And so mathematically, it means we need to compute a singular value decomposition of this matrix. Well, for a high-dimensional system, we have been very much limited computationally because it's very expensive to perform this singular value decomposition for the reason that usually we use iterative methods where you actually integrate the operator. So in this case, for each integration, it's a forward and one adjoint integration. And you do that in sequence until you reach the desired dimension. And so now we can use newly developed randomized SVD algorithm when we fully parallelize the process. And so instead we run parallel independent integration starting from random vector. And so you can say, if you look at n singular vector, for instance, you need n iteration for the former approach, iterative method, and now you can divide by n, basically, the computational cost. So it has many applications for optimization, posterior error variances, estimation, and error tuning. And so I'm going to present that quickly. One by one, I will start with the information content analysis. So once you get this singular vector decomposition that you efficiently computed, each of those eigenvectors represents the mode or the spatio-temporal pattern, if you wish, of your emissions that are most constrained and independently constrained by the observation. So on the left here, I'm representing 3 of those modes. Okay, so you have a mode that corresponds to, I believe it's Toronto here, a mode that corresponds to the California hour, and one the Appalachian. And on the right, you have the corresponding mode in observation space. So the exact observation that actually constrains those patterns. So you can use that for posterior diagnostic to interpret your results, but also to do some aggregation of observation. Like, let's say, satellite observation, you can reject or filter the observations that are not needed for regional inversion, for instance. So this is a couple of application of that. Now, if you look at as I said, it's much more efficient, that iterative method to minimize the cost function. So I'm showing an example for methane inversion here. On the left, the BFGS minimization using 4 iteration, which took 2 days roughly. In the middle here, this is using the randomized SVD I just described. And so you see that it took a bit over 1 hour to get similar results with this method. And then another very interesting feature of this method is that then you can have a low-rank representation of your posterior covariance matrix, and you can use it to sample the posterior. So on the right here, I'm representing independent realization of the posterior. And if you look at, for instance, Florida here, you can very well see the correlation, spatial correlation pattern as you see the movie, basically, of this sampling. And so it's very hard to represent correlation on a 2D map. You really need to have a sampling method to really see the features and understand what's going on. Okay, so another interesting aspect is that given that it's very much more efficient than the iterative algorithm, you can actually compute many more modes, right? And so we did a test with it's a work by Kelly Wells in the University of Minnesota. She did an inversion of monthly N2O method. Well, actually, that's an error. Yeah, N2O monthly inversion. Sorry. And so this is the results on the left for 4 iteration. in the middle for 40 ensemble of the randomized SVD, and on the right, 100 ensembles. And so you see that if you look at over Eastern US, the Eastern US, for instance, you have a negative increment for the rank 40 results. But if you include more modes, actually, you can get significant differences with even a change of sign in the increment. And this is also something you see over Central Africa, where you get, including more modes, actually dramatically modify the increment at the end. How much time do I have? Okay. So like 1 minute, 2 minutes?
I'll give it to you.
Okay, so I will finish quickly. So the last method, we can also efficiently perform error tuning. So starting from some prior, which might not be the true prior, we scale it until we match some criteria. And usually, to match this criteria, we need actually some iterative method when we need to do one full converged minimization for each iteration. With our method, we can do that at no additional cost because we don't change the initial singular value decomposition. So it's done at no additional cost. And so I did some pseudo experiment when I start from the prior error. And you can see that with a 1K projection, I can actually reach convergence pretty well. And on the right here, this is the impact. This is a scatter plot of the true flux increment versus the corrected increment. So in black, when you use the wrong increment and the corrected one in red. So you see that you can very much improve the estimate in the increment itself when you actually tune this prior error. And I will just let the conclusion. And take one question maybe, but I don't know if I have time.
So, Nicholas, I couldn't quite tell, when you do the, say you split off at 5 modes, so you're doing this spectral analysis, what's the remaining error just from representation? So if you just use 6, 10, whatever the optimal modes are, you're going to get the optimal amount, but you are going to get an error just because you're only representing, you're not representing the entire spectrum.
No, so that's the big advantage of this method. That this projection, with this projection, that's the only one actually that allows us to actually remove effectively the representativeness error. And so that's the big advantage of it, because you cannot actually, in fact, there is no way you can represent the representativeness error for a large high-dimensional system. And so we don't actually need to form this representativeness error matrix in this case. This is like one of the fundamental properties of this projection. We can just get rid of it. Yeah.
You still get a representation. Whatever the world is, even if you can't represent it, it's still there. So you should still get some kind of error term based upon whatever amount.
We can discuss afterwards about that, but what you call the representativeness error is actually, we fix this problem with this method. We effectively don't have a representativeness error. Yeah, we can talk about that.
Thanks. And now it is time for poster introductions. So if everybody could come up, that would be great.
Slideshow mode?
Yeah, and then just press pause. If you need your order here.
First one.
Oh, no, you're second.
Thank you.
Yeah, you're second now.
Okay.
Because Yang Feng is...
Actually,
Yeah, you're back. As it turns out, once again, 2 different people. Some commonality in their names.
So,
okay.
We'll go slideshow and just press pause.
So, but where's the one before that?
Yeah, sorry. Okay.
Okay, there you go. Okay, perfect. We got it. We got it. Yay! There you go. Look. Okay.
So I just skip the first part to just focus on what we have done. Basically, we develop a target model for the Bowman phone and dipole methane by linearizing the chemical and photochemical degradation based on the offline 3-hourly OH field and the photo necessary. So we use this model, we cannot estimate the surface fluxes by assimilate the aircraft measurement by cast and contrast. So basically what we found, oh, it's over.
Hello, I actually have a specific title here, not a very general one, and the post number changed to 8.16. Compared to the whole column XCO2, the lowermost troposphere partial column is more sensitive to the variation of surface flux. Inversely, the estimation of the surface flux could possibly improved by...
Switch. Okay. I'll be quick. Hi, so I'm Kelly Graham. I am working with Chris Holmes down at FSU, and so we have gotten our hands on this exciting new data set of Arctic air chemistry and meteorological measurements. And so we've evaluated Merit-2 meteorology at several resolutions and have done some preliminary modeling with GeosChem. So if you'd like to learn more, my poster number is A17.
Our board objective is to quantify the sensitivity of CO2 flux estimates to the underlying biospheric CO2 flux models. Here we have four forward model simulations using 4 different state-of-the-science biospheric CO2 flux models. Our results show greater than 5 ppm difference in XCO2 between OCO2 and GeosChem, which will have an impact on the top-down CO2 flux estimates.
So my research focuses on the sources and sinks of different carbon greenhouse gases. So we use measurements from different platforms across Australia, interpret them with GeoChem in order to identify different sources of these gases and their latitudinal variability. And we do this in order to reduce the uncertainties in processes driving atmospheric composition and, of course, emission estimates. So if you're interested in these plots, come and look at my poster. Thank you.
So in my work, I will talk about transport biases in GeoSchem model. In particular, I will explore the origin of the reduced vertical transport at the coarse resolution and show impact of the increased numerical diffusion. I show that satellite observations, particularly GOSAT, can be used to diagnose transport biases and can remove some of them. And I explain why coarse resolution model, particularly 4x5, is not desirable for flux estimation, such full flux estimation. However, it can be applied for.
So I'm Alex Turner, and my poster is on some decadal trends in atmospheric methane, which is a topic that's received a lot of attention recently, with some competing hypotheses being fossil fuels and tropical livestock. And so if you're interested in either methane trends or actually how hydroxyl might have influenced those, come by my poster.
Hi, I'm Jianxiong Shen. I'm a postdoc with Daniel. So my poster is about trends in North American methane emissions and inferred from satellite data. We found significant increase in the U.S. methane emissions with contributions from both oil, gas, and livestock. So for more information, please come to my poster. Thank you.
Right. We are working towards a policy-relevant methane emission inversion. We're starting off from a state-of-the-art prior emission inventory, included our gridded EPA inventory for the United States. And we then combine it with the full GOSAT data record. And our inversion doesn't only give average emission scaling factors, shown on the left, but also grid-level trends and annual global OH scaling factors.
Have you ever wondered, what are the changes in air quality in my region? Have you ever wondered, how do those impact the climate? If you want answers to some of those questions, come visit my poster.
We conduct a series of observation system simulation experiments on the GeoSchem weak-constrained 40-var data simulation system using carbon monoxide pseudo observations. Results show that compared to the strong constrained 40-var approach, model transport biases are captured and greatly mitigated in the weak-constrained system. Thanks.
So we have developed a tropospheric chemistry data assimilation system using ensemble Kalman filter technique and the geoscan model. So assimilation of test ozone data shows the improved agreement with the independent observations. Then using this system, the multiple species measurements are assimilated to optimize the various emission sources and to constrain the entire chemical systems. So these assimilation results will be compared using the 3 different chemical transport models and against whole river analysis.
We have tested JustCam on cloud computing platforms. This new technology allows you to launch a server in cloud and run JustCam immediately without having your own machine. And the system will be correctly configured, so you don't need to spend any time on software engineering, and you can just do the science. And 1 month's benchmark simulation only costs about $1, and you can request any amount of CPUs you like. But it only works for the version 11 and not for GCHP yet. You can find the tutorial online. Thanks.
Hi, my name is Irene, and I'm going to, my poster is on the development of the GeoSchem adjoint for the Unified Chemistry extension. So I'm going to speak a little bit about what modules we're introducing, as well as the reason we're introducing them, which is to quantify the impacts of supersonic aircraft which fly in the stratosphere, and their emissions are fairly uncertain at the moment.
All right, let's have a round of applause for them.
So thank you to all the poster presenters, for all the session speakers. Just a few logistical announcements. So we will have the nested model working group convening in Pierce 301. That's a building next door at 5:15. And we will have your joint clinic just upstairs in Maxwell Dorkin 119. Maxwell Dorkin joins you. You just go up the stairs. You can't miss it. You're welcome to stay here for a while. We need to vacate this room at 5:30. There's a class coming in, so make sure you pick up after yourselves. We have a lobby for the whole evening. So the poster session formally starts at 6. So first, you're welcome to hang out